excuse me, definitely one of the more intensive classes that we're going to have on the O'Reilly platform is talking about kind of where is deep learning today being applied in many areas of AI. So to give you a quick rundown of what is going to happen today, and I'll get into a little bit about myself in a second, is we're going to spend the first hour roughly just talking about deep learning in general, what it is, what are the big words you'll need to know. People have PhDs in deep learning and deep learning applications, like very specific areas of deep learning. So of course, we're not going to get super deep into all of the math behind deep learning, because I want to spend a majority of the time today talking about the various ways deep learning is being applied across AI, both text-based, multimodal, reinforcement learning, and how we are able to both benefit from other people fine-tuning their deep learning models, and also taking a look at how we can fine-tune deep learning models for our own benefits as well. So it's going to be mostly a survey of, a pretty in-depth survey, meaning I'm not just going to tell you something is true. I'll actually show you some code on how to get it done. Our GitHub is pretty large, and I'll share my screen eventually a little bit later, and I'll kind of walk you around. But you'll also notice that we have over 200 slides. I think it's like 220 slides today. The goal is not to get through every single one of those slides. In fact, I'm already doing a terrible pace if that were going to be true, because I would need to spend at most 45 seconds on each slide. But rather, they're there to give you more context if you want to go back and look at more. There's going to be more examples that I'll have time to go through. Again, that's on purpose. The code's in the GitHub. It's in the slides. I just want you to have as much as you can possibly have to understand deep learning. I myself am a former theoretical mathematician. I taught math and computer science and data science, mostly math and data science, at the Johns Hopkins University in Maryland, in Baltimore, Maryland. Long story short, 10+-ish years ago, I wandered into the field of AI machine learning from theoretical mathematics, started a company, which ended up being one of the first language modeling companies in the enterprise back in 2014, 2015, roughly a good 7 years before ChatGPT existed. So I have a lot of experience training deep learning models, specifically as language models for the enterprise, and I still do that to this day. So I am going to be coming at this both from a theoretical angle of here's the basic underpinnings of the math that is binding all of the deep learning applications today, but also from mostly a very practical standpoint of here's where the deep learning actually surfaces so that we can see what the commonalities are, but how each individual kind of tweaks it and creates their own version of a model for their particular use cases. Cool. Blah, blah, blah. I have books and videos. If you'd like to look more into them, I'd be really appreciative, but that's not really the point of today. So let's get started. All right. So we're going to talk a little bit about deep learning and PyTorch, PyTorch being the framework in which we're going to implement most of our deep learning today when we get to our code. Oh, and by the way, sorry, one housekeeping note I forgot to mention. If you do have a question or a comment for me, I would actually prefer that you put them in the Q&A widget, the Ask a Question widget, I believe it's called on your end. I just have that open when I'm looking at my slides at all times, so I can see if someone has a question very relevant to the slide I'm looking at, or just a general question. If you can put it in the Ask a Question widget, even if it's not a question, technically it's just a comment. If it's directed very specifically at me, I would rather you put it there. It's just going to be easier for me to see it, archive it when I answer it, so I can make sure as many questions get answered as possible. Okay, that was it. All right, so I'm willing to bet that a lot of you have actually heard the term deep learning, or even more so actually used or built a deep learning model in the past. Usually what ends up happening in these classes is that there's a healthy mix of people who are just curious about deep learning, some people who are actually trying to fine tune some models, and people who are just kind of figuring out what they don't know so that they can get a better sense for what they do want to take as a class at a later date. So I'm here to accommodate as many of you as possible, as best I can. So what is deep learning? Big question, frankly, a very big question with history going all the way back to the late 20th century, the 1970s and the 1980s. Machine learning and AI itself predates that. Arguably, the first machine learning models, which were basically just statistical models, were put forth in the 19th century, but really formalized as a field of research as machine learning in roughly the 1940s and the 1950s. Now, fast forward a couple of decades, again, roughly the 1970s, 1960s, 70s, 80s, again, it kind of depends on how loose of a definition you're willing to go with here, is the introduction of deep learning. Now, the basic terminology you'll have to know is that machine learning, very broadly, again, very broad definitions here. Machine learning is a branch of AI, a simulation of intelligence that focuses on learning from data. That sounds almost trivial, like of course it does, but that wasn't necessarily trivial a couple of decades ago. Before we had machine learning, we had things we had basically heuristics, rules-based intelligence. You know, if you can imagine a computer game navigating a maze, an NPC, a non-playable character navigating a maze, that's not machine learning. That AI, quote unquote, in the game did not learn from previous data. No, it was given rules on how to navigate a maze by a programmer, and it looks pretty intelligent when it's able to solve the maze. So machine learning basically says, well, I'm going to teach this intelligent behavior or semi-intelligent behavior through data. I'm going to show you examples of what it is that I'm trying to do, and then you're going to learn from that data. Now, that machine learning, of course, could be branched off into several different areas. We're not really going to get into that today. Instead, today, we're going to focus primarily on one particular subset of machine learning called deep learning, where it is a subset of machine learning, meaning deep learning itself is machine learning. It is algorithms learning from data. So that's still true. That's just machine learning in general. The difference is that deep learning is specifically architected around what we call neural networks. Let me clear the screen here. Neural networks, which is, again, itself a bit of a broad term, but very high level, the concept of a neural network, and I'll show some more defined illustrations later on today, is basically interconnected layers, and that's going to be a key term today, layers of computation, often called neurons, although the conflation between a brain neuron and an artificial neuron is, it's a very common one. Obviously, the obvious analogy is, this is basically how neurons pass data to each other in our brain, which, the key word there being basically, meaning, sure, at the highest of 101 levels of neuroscience, sure, but neuroscientists understand a lot more than just these artificial neurons, and basically our organic neurons are doing a lot more than what the artificial ones are doing. Now, that all being said, the concept of deep learning is, if we string together enough of these neurons, and each of these neurons, oops, I didn't mean to do that, each of these neurons is basically running a single, what we call linear transformation. What does that mean? Basically, what that means is every single neuron is mapping data from some X to some Y. Now, in the very beginning of the neural network, that X is our raw data, and we'll talk about what that raw data could be, meaning text, images, videos, whatever it might be. And it maps it to some other vector space, Y. If you're familiar with the concepts of domains and ranges, functions, which map from A to B, from X to Y, these general maps or transformations of data is in every single neuron. The very, very broad concept of deep learning states that if you string together enough of these transformations, meaning if you have something that goes from X to Y, and then something that goes from Y to Z, and then something that goes from Y to Z1, Y to Z2, and you keep going, eventually you've effectively created a map from X to Z2. And the theory, again, the very high level theory is, well, let's assume X and Z2 are anything. If X is text and Z is some other text, all we really need to do is figure out a bunch of transformations, very micro transformations, that eventually get us from X to the thing we are trying to predict. Which is why a lot of the running joke, if you will, the inside joke of deep learning is that it is the field of approximating any function on the planet. If you can name a function, you can architect a deep learning architecture to approximate, keyword there, approximate that function that you are looking for. Which is why today, deep learning dominates a majority of all of our AI fields today. Image generation, video generation, obviously things like chatbots, agents, large language models, even going as far as reinforcement learning and things of that nature. All of the underlying architectures that we use for these endeavors are deep learning models because of that unifying promise. If you have a function, a map that you are trying to relate, if I talk to this robot, I want this robot to move its arm. That's a complicated function. So if you split that function up into several, in many cases, hundreds of thousands or millions of little transformations along the way, you can approximate that map without having to directly learn something that goes from the input to the output. So obviously I'm high level hand waving a lot of this. So let's go one level deeper. So that neuron that I just described is pretty much the fundamental processing unit of that neural network. Each one of those neurons does a linear transformation. Now, if you're not a linear algebra buff, which I'm not expecting anyone here to be, again, we're not diving too deep into the math here. I've proposed that class before and it was rejected, but we're not getting too deep into the math here. The reason why I keep saying the words linear transformation, and perhaps some of you are thinking, well, what does he mean by that? I thought it was all just a bunch of weight matrices being multiplied by data and potentially adding some bias vector at the end. It is. There's a fundamental theorem of linear algebra, which is one of the things I taught back in college, which is why I like deep learning so much, quite frankly, I think, is that a linear transformation, very nicely, which is very nice for mathematicians, can be expressed by a matrix multiplication. So this weight matrix actually is doing the job of going from Y to X. So this weight matrix is exactly the definition of this map here. And this B, which is often referred to as a bias vector, which not necessarily meaning like error or a bias in, sorry, let me rephrase that, not necessarily referring to a stereotype kind of bias or a prejudice kind of bias. Here, bias is being used in a more mathematical sense where it's error. Bias, quite literally, is simply an error in some model. So you account for this error. Again, this is an approximation. The weight matrix exactly defines a linear transformation. The bias vector is there to kind of pick up the slack of, well, there's going to be some level of error in this map of this greater arc of trying to go from X to anything, map anything to anything. The bias vector is there to basically pick up the slack, if you will, of, well, if the transformation can't account for all data, this bias is going to kind of move things around a little bit to be as close as possible from X to Y. Because again, this is all an approximation. There is no, potentially, function that perfectly maps text to text. But we approximate these functions in many different ways, which is what gives us many different methods of doing things, something like GPT. The question coming in from AA, will I get into the new JEPA and VJEPA architectures by Meta? Short answer, no. I'm so sorry, AA. They're a little too advanced, I think, for what we're going to be doing today. So I appreciate you asking up front if that's what you're really hoping for. No harm, no foul. But for those of you who are curious, JEPA and VJEPA are you guessed it, deep learning architectures, which specifically are in this realm of what are called world models. And by the way, keep these kinds of questions coming, please. If you're curious about a specific kind of deep learning model, and if I'm going to get into it, please do ask. Specifically in this case, no, I actually do talk about JEPA and VJEPA in my AGI lectures, because it is, in some people's minds, the next step on our pathway to AGI. But at a very smaller level, or rather a more succinct level, JEPA and VJEPA are simply more modern deep learning architectures with a specific task. The map that they are trying to approximate differs from company to company. But Meta, who at the time when JEPA was being created was being led by Jan LeCun, or at least the AI part of Meta was being led by Jan LeCun, he's had this, radical is a strong word, but very strong argument for a next generation of AI models, which he would call world models, which instead of mapping very, very tight domains like text to text, image to text, text and image to text, he would basically say, well, what if we consider the entire world as the map? And we have to teach this thing to simulate what the world around us will do given a scenario. If there's time at the end, I'll show some screenshots of like the actual JEPA architecture on my screen here. But for the sake of our slides today, I am not going to get into that specific architecture, but thank you for asking. Okay, so those weights and biases, the W's and the B's, are going to effectively be our micro linear transformations along the way. So when we talk about layers, what we're really talking about are each of these little circles here, each of these is a map. Each of these has a weight and bias. Each of these little neurons here are going to have a weight and bias. So what's actually happening as data passes forward, in this case from left to right, is the input data is your raw data, as raw as the researchers allow it to be. There's this concept of pre-processing in which you massage the data a little bit, but the researchers define upfront what the input of the model will be. And then we'll see examples. It could be pixels, it could be text, it could be, again, in theory, anything. But you have some raw data as your input. Your neurons will perform operations on each individual unit of data. For example, you might have text being broken up into tokens. You might have images being broken up into pixels or small little patches of images, as we'll see in one architecture a little bit later. But then once it creates, or rather runs that linear transformation, to continue our analogy, this arrow here, for example, this arrow here represents a single map, or rather these arrows coming out of this neuron, I should say, represent a single WX plus B, a linear transformation plus some bias. And bias is technically optional. I should be clear about that. So not everybody uses a bias vector. Some people just use a weight matrix. Again, going off of the assumption that a weight matrix is itself the linear transformation. It does not require a bias variable. Again, these are decisions that researchers get to make when they are creating their architecture, but I'm kind of speaking broadly here. These arrows represent a linear transformation from this neuron, and it outputs a whole vector of data, a whole bunch of data, and it passes that data on to the next layer, where itself will also do its own calculations, which is with its own weight variables and biases, and go through all the layers, keep going. So the input of each layer is the output of the layer that came before it. Again, going off of the analogy that, well, neurons link everything from my fingers all the way to my brain. So when something hits my hand, that signal has to crawl up my arm effectively to my brain as quickly as possible. So these interconnected neurons basically represent the pathway of raw data through some processing unit. Now, where the analogy breaks for a lot of people is, well, if the neurons are sending data up to my brain and these neurons represent the same thing, isn't this whole thing just my arm, question mark? Where's the brain? I thought the whole model was the brain. And this is kind of getting back to VJEPA here, and kind of the next generation is, well, if we're going off of this analogy, the arm, the layers here mapping raw data to something have to lead to some bigger brain, meaning it has to basically pass through these layers to get to some bigger central processing unit. But that is, like I said, a much more modern take of deep learning, which is not what most people do today. So we'll be talking about what most people are doing today. All right, a couple questions here. Neurons from neurons and are stored as millions of variables. Parentheses, vector databases. The model is a set of layers, question mark. The storage of model is based on vectors, question mark. So a lot of questions. These parameters, the weights and the biases, all of these numbers, because again, a matrix is a row by column organization of numbers, as is the bias vector, which is a one-dimensional series of numbers. They're not stored necessarily in vector databases, as your question says. Those are specifically, I mean, colloquially in the market, used to mean for things like information retrieval. But quite literally, when you go to, I'll actually share my screen for a second here, just to help answer this question a little bit. Okay, sharing my screen for the first time today. You won't be able to see me. That is on purpose. If you go to the world's largest repository of models and data, Hugging Face, for example, and you go to really any model, I mean, here, let's take this Quite 3.6. What are the most recent? 36 billion parameters, which means if you go into these files, you'll see that a majority of the repo is dominated by what you see here, this model 6 of 26. Each of these is a subset. It's not the whole thing, but each of these is a subset of all of the weights and biases values that were learned during training. And we'll get to training a little bit later, but right now we're just talking about the architecture. So it's hard to kind of see them in Hugging Face here, but each of these is a map. So for example, this map of 32 by 2048 represents a projection from a dimensional space of 2048 mapped to a vector space of dimension 32 dimensions. So each of these represents or most of these, some of these only have one number, are vectors and not matrices. But the ones that are matrices, which have two numbers in them, they do represent, again, they call them weights here for a reason. These are the weights of that linear transformation. So they're basically projecting from one dimensional space to another. So this is so if they're not vector databases, they're literally just files. They're literally just files of matrices, which store a lot of numbers inside of them, to be very clear. There's a lot of matrices in here. For example, this matrix here is, if you hover over it, 16 million parameters, which is not by coincidence, 8192 times 2048. There are 16 million numbers inside of this one matrix here at the, as you can see here, 23rd, it's a zero index, 23rd layer of this deep learning model. This weight matrix of this microlinear transformation is itself 16 million parameters, or 0.98, so roughly 1% of the entire model itself. So it kind of goes to show that these numbers did not used to be so big, meaning deep learning models from even, call it 10 years ago, I'll stop sharing here, from 10 years ago, none of them got even close to 1 billion parameters. And now the kind of the mid-level tier starts at around 25, 30 billion parameters. So there's an argument to be made that deep learning models have really just gotten bigger over time, which obviously means that they've gotten more capable. ChatGPT, when it first came out, was, no one knows for sure, but roughly 175 billion parameters. And that was November of 2022. Now, most models, frontier AI models at least, are arguably, again, rumored to be over 1 trillion parameters. So these things are just getting bigger as we shove more data inside of them. Okay, so I hope that answers your question. Two more questions, and then we'll move on. Where is the matrix? What is the matrix used in the transformation? Where is the matrix used in the transformation? So the where I just showed you in there, but what is the matrix used? And I'll merge this with someone else's question. MP asks, why do these parameters matter? These parameters are those microlinear transformations. They are the components of the mapping anything to anything. You learn those parameters. So you're at the question of what are those maps? Those maps need to be learned. When you initialize a deep learning model, which is a term of art, meaning you bring it online for the first time. When you initialize a deep learning model, you set every single parameter value to a random number. And there's even theories about the best way to set them randomly, which we're not going to get into today, but you set them randomly. Meaning, when you ask GPT a question, before it has seen a single bit of data, it will give you complete gibberish. It is not born with any knowledge whatsoever. Those parameter values must be learned through data, which leads us to this slide, gradient descent and backpropagation, which is itself, I mean, if you Google this, you might find an hour-long video on YouTube just on this topic, if not longer. So I'll do my best to compress it so we can move forward rather. The concept of gradient descent and backpropagation is as follows, and there's a couple terms we'll need to note here. First term I'll actually define as loss function. I might want to flip this in the slide. Loss function is literally a math function. We'll see examples of it in our code, in our first coding example. A loss function quantifies, effectively, error, the difference between the model predictions and the ground truth. So we have to give these AI models data, which we know what the right answer is. So we have to give it a piece of data, ask it effectively, what would you have done in this situation? We have the right answers as humans, and we compare the model's answers with the right answers. For example, in terms of a language model, you might give it a paragraph, and a paragraph that has already been written. You remove the final word and say, what word is this? What word should go here? I know the answer, but I'm quizzing you, AI. What do you think the last word should be? It will give a guess. I know the answer. I compare those things, and the way I compare those things is through a loss function. A loss function is an error function that goes down when the model is better, because loss is incorrectness, error. When loss is down, it means the model is getting predictions more in line with what the ground truth, the answer, was. So the whole point is I give it data, I know the answer, I quantify its error using a loss function. So then the point of deep learning, the way that these things learn, is to find, and this goes back to why do these parameters matter, or what are these matrices used in the transformation? We don't know. Up front, we don't know. They have to be learned. What you're looking at, this image here, is a three-dimensional graph with 3 dimensions, x, y, z. Think of all of these as parameters. So imagine the world's stupidest deep learning model with only 3 parameters in it. Okay, so again, 3 versus tens of billions, hundreds of billions, trillions. In this example, it's 3. So to kind of give you a sense of the mathematical scale for what researchers are kind of dealing with, imagine a model with only 3 parameters. It can be done, it would take infinite time, but it can be shown that for any possible parameter value, what if z were 2? What if y, the other parameter, were 0.5? And what if x was 0.75? What if? So if I were to randomly set these values of the parameters inside of these matrices, I can compute a loss value. And this curve on the screen, for example, if there was 2 y's, it might be around here, the numbers I just circled. This is our loss function. Every single combination of parameters, if you set them in that value, given those values, you can calculate a loss value by shoving in data for which I know the answer to, seeing what the model would have done, seeing the difference, and plotting that on a graph. So with only 3 parameters, you end up with something that looks like this. This is effectively, the fancy term for this is a manifold, but it's basically a loss curve in 3-dimensional space. So how then do you get these parameter values? Well, when you randomly initialize your model, you have a starting point, which in this graph starts at around here. So here's where we start. This is random parameter values. And I mean this very sincerely. Even the top researchers at Google, Meta, Apple, X, wherever, even the top researchers will tell you, yeah, you just have to start in a random spot. You just have to start somewhere randomly and try to get to the right answer. This is a fundamental truth of deep learning, which is these things are not born with anything. And again, caveat to that is some fields of AI focus specifically on, can you randomly generate parameters with some knowledge as a head start? That's a whole separate field of AI that we can't even get into today because, frankly, it's not used by most people. It's not mature enough. Most people just randomly initialize their parameters to obtain an initial loss. So then we have to make the model better. That is done through something called gradient descent, which is, again, big picture, the iterative process. And iterative, I'm going to highlight here. Iterative. It is not a single function. It is not a elegant, well, okay, it is elegant. I should not say that. It is not a fast operation. It is not a one-shot math formula. It is an algorithm in which you do things in batches, in steps. It's iterative. Every single time you want to train your model, you will follow the following process. You will first, clear the screen here, you will first get a batch of data. Again, you know the answer to all of the data. There's an X, there's a Y, there's an input, there's an output. I know what the answer is. You give the AI the inputs, you compare the AI's outputs to the ground truth outputs, you get a loss. As you are doing this, as the data flows through the model, the system around it, which in our case is going to be PyTorch, the framework around it, has to remember all of those calculations it did. And I'm going to hand wave away a lot of calculus in just a moment. It's going to remember all of those calculations. Why? Because at the end of processing that data, we've compared it to the ground truth, we have a loss. That loss is a number. It's a scalar. It's a single number. It's like 5 or 4 or -5. It's a number. But that number, you want it to go lower. So to make it lower, you basically have to update all of the parameters, wiggle them tiny little bit, change this one z from 1 to 1.01. This one goes down a little bit, this one goes up a little bit, this one goes down a little bit. You have to know how to move all of your parameters just a little bit so that your loss would have been better for that one particular batch of data. The algorithm to figure out what those minute changes are is called backpropagation. And if you are someone who is well-versed in calculus, backpropagation is very little more than what we call the chain rule in calculus. So once you remember that all a deep learning model is one map after another, you can basically say, well, if this whole thing we call f, our function, then if we want to find the change of that function, the derivative, with respect to all of our different parameters, which is often written as theta, parameters of a model, this can be done by, figuring out the derivative of z with respect to y times the derivative of y with respect to, you go backwards, and then you can change each parameter given that calculus formula, which again, that's where I'll kind of pause on that math there. So you go forward with a batch of data, here's a term of art, accumulate the gradients, meaning PyTorch or TensorFlow or whatever framework you're using remembers all of those micro calculations that you're doing so that by the end, you tell it backpropagate. This was the loss that we got. Change the parameters so that your loss goes down a little bit for that batch, and then move on to the next batch of data. So every time you move on to the next batch of data, you have a slightly different set of parameters in which you can recalculate your loss, reaccumulate your gradients, re-backpropagate, and this is the iterative nature of gradient descent. You run a batch of data through, calculate your loss, use calculus's chain rule on that loss function to figure out what the change in parameters should be to lower the loss. And if you are itching for more math here, I would urge you to Google things like chain rule or directional derivatives. These are kind of Calc 3 terms that we'll have to fly by for now. But you go backwards, you change your parameter values, and then you do it for another batch of data. Last thing on this slide is when you do this process, you have to make a lot of decisions up front. To put it mildly, you will have to do, for example, what loss function? There are, I kid you not, hundreds of loss functions. That's conservative. There are conservatively hundreds of loss functions to pick from. Which one should I use? I'll show you an example of picking them a little bit later. Okay, gradient descent technically has variance as well. Are we doing batch gradient descent, stochastic gradient descent? There are many ways of actually mini batch gradient descent. There are many ways of implementing gradient descent. Even backpropagation is, well, okay, backpropagation is actually one of the few things you can control because it's just kind of the chain rule, it's just kind of calculus. However, there are still hyperparameters to control how much propagation, or rather how much change in the parameters there is. Learning rate is one of those what we call hyperparameters that we can decide. A hyperparameter referring to the fact that the parameters are the matrices inside of the model. We don't get to just decide what those are. They are learned via data. But a learning rate is a number we can choose. Like a human being sits down and says, the learning rate is going to be 2 times 10 to the negative 5, which is a very common learning rate. If you ask an AI to make a deep learning model for you, it will almost always choose this learning rate, to put it another way. It's a very common learning rate, very, very small, as you can see by the number here, and it controls how quickly you move down this manifold. Because, and I know I'm spending a lot of time on the slide here, but this is kind of the core of the deep learning here. You could say, Sinan, in fact, I'm curious if someone has asked this, there's a lot of questions coming in. Not yet, but one common question I get around this time is, well, hold on, this seems really simple. Said that, no, I'm not, okay. This seems pretty simple. If you have an initial area and you can see the manifold here, obviously you can just go down to the bottom. 2 problems. 1, you can't actually see this manifold. Like I mentioned before, this is a almost stupid example of a deep learning model with 3 parameters in it. You can't visualize this at 16 billion parameters. You just can't. And in fact, to calculate this manifold, you have to effectively calculate each individual dot and then string them together in a visualization software. So that's out of the question. You can't really see this manifold. You don't really know exactly where you're going. The other problem is, well, you also don't know, this manifold goes on forever in theory. What if I go 5 units this way, all of a sudden it plummets even more. So there's a lower loss value over here. Because you can't see the manifold, you have no idea whether or not the thing you are going towards is either a local versus a global optima, or in this case, minimum. You have no idea. And when I say you, I mean the top researchers on the planet also don't know. This is effectively an educated guess for them. So what do they do to get around this? They'll actually do this whole process many times to say, well, let's initialize the model randomly 15 times, train them all the same way using gradient descent, and see if we keep getting roughly the same end performance. Because if you do, that would be a sign that what you are approaching is the best you could actually do, because we keep trying it from different locations and we keep getting to roughly the same level of performance. What learning rate does is it controls how quickly you make a step. Because you don't know where you're going, you can't see the manifold, you don't know if where you're going is the best place to go, you take really small steps every single batch. So the learning rate controls how much you move every single batch. Too much, you might end up completely missing the minimum and ending up somewhere else on this manifold, kind of, Interstellar style with Matthew McConaughey. You miss the wormhole a little bit, kind of circle around it, and then you end up somewhere you didn't want to be, which is also true in n-dimensional Euclidean space. So if that's possible, then you want to make sure you take tiny, tiny little steps to get there. Of course, the practical problem with that is, man, it's slow, which is why it takes, no joke, weeks, if not months, to train some of these huger models with billions, trillions of parameters. Is to do it right, you have to go slow. To do it slow, you have to spend money and time. That's just the trade-off you have to make in deep learning. Okay, let's get off the slide. A couple questions here that are directly relevant. What's the difference between gradient descent and smoothing? A lot. I mean, gradient descent, smoothing has nothing to do with, smoothing is not an optimization algorithm. Smoothing is more around adjusting the parameters, not for the sake of lowering your error, but for the sake of making some future calculation a little bit easier or more likely to impose basically a rule. Meaning, well, look, for a very common example of smoothing would be something like, oh, I want to smooth out my parameters here so that none of them ever actually become 0. They only ever become close to 0, for example. So it's not necessarily to increase the performance of the model, not always at least. Sometimes it's more to impose a certain structure that the researcher thinks will help, but it's not one actually learned through data. Someone's asking about text and tokens in other languages. We'll get to LLMs a little bit later, LA. So I'll the same LA from the Catalyst, I wonder, from a couple of days ago. Who knows? But we will talk about LLMs a little bit later. A couple more questions. Does gradient descent have only one low point? Oh, okay. I think you probably asked that before I said the answer out loud, which is A, we don't know, but B, probably not. In theory, again, Albert Einstein theory, yeah, there is technically one lowest point, or at the very least, multiple points with the lowest loss value. But again, it is computationally intractable, which is a fancy word for saying impossible. It is computationally impossible to check all possible values to technically know if that's true. But theoretically, yeah, the manifold does have a lowest point, which many parameter values might share, but one definitely exists. We just don't know where it is. We have to find it. How many iterations? Is it thousands? That's going to be a huge range. When you're starting from literal nothing, like initialization of a model, easily thousands, more, quite frankly, like probably millions, quite literally, if you're starting from scratch at a large enough model. When we get to our fine-tuning section today, and we talk about transfer learning, we'll find that when you break up training into multiple phases, you actually can reduce the number of steps needed to find that optimal answer, which is good for us, but it does not really help the researchers so much. A couple more questions. As the model already knows the responses, is the process of obtaining the responses called prediction? I think a good clarification here. The model does not know the answer. I know the answer. The system knows the answer. The model only has X. The model is given the input. The model's output is often called Y hat or Y bar. This is the prediction of the model. It is then compared to Y, which is our ground truth. So the model never actually knows the answer. It only outputs a prediction, an approximation. And we tell it, you were this close via the loss function. You were this close to the actual answer. Update yourself so that the next time I give you that same X data, your Y hat will be closer to Y, which will yield a smaller loss value. I hope that helps. I know there's more questions here, but and I'll hopefully get to some during our break, which I'll try to take every hour. So our backend, if you will, our framework for performing deep learning today is going to be mostly in PyTorch, which again, I don't want to sell you too much on any particular framework, but PyTorch is just very common. It overtook TensorFlow, which was the most common deep learning framework 10 years ago. Yes, I'm old, I know. But PyTorch is right now the most common, both research and practical. Most like Hugging Face's Transformers package, which is the world's most used open source package for manipulating open source and open weight LLMs, primarily works on PyTorch, and it was originally only worked on PyTorch. Now it's expanded to work with multiple backends, but PyTorch is preferred. Why? 3 reasons. 1, it has something called eager execution, meaning it has a way of efficiently storing the parameters of a model so that your GPU, your RAM, your in real-time memory, the thing holding the model in memory, requires less memory to run the same model than, for example, on TensorFlow. Second one is autogram, which is this one's for the mathematicians. Remember when I said earlier that the framework has to remember all of those gradients, accumulate them so that it can perform the backpropagation algorithm? That's what it's just very smart computer scientists who understand computer science way more than I do. I will not ever claim that I know computer science better than I know math, but very, very good computer scientists talked to very, very good mathematicians and figured out a way to very efficiently, computationally, do that backpropagation exactly without any approximation, but while using as little memory as possible. They called it autograd, automatic gradient accumulation. And it's to this day the standard in how backpropagation can work computationally. And then, of course, like any other framework, it has the ability to hook into GPUs for more efficient calculations and computations. But this is not necessarily new or rather unique to PyTorch. But it is basically the third thing that you kind of care about is I can hook in a GPU to make these computations more efficient. So, and because it's so popular, it has a lot of pre-built modules baked in. So you're almost never starting from scratch. We'll actually see some PyTorch documentation at our first I already said this at our first screen share. All right, which we're about to get to our break and a little bit of screen share and a couple more slides here. So when you fine tune a machine learning model, I didn't say deep learning. Remember, I said machine learning, which is a superset of deep learning. So for any machine learning model, deep learning or not, this is the general path you want to follow. And I'm going to use these terms later on, so I want to show them to you. You generally start with a batch of data. No surprise, right? Machine learning requires data. You split that data up into 3 sections: training, validation, testing. Some people might refer to these as different names. I'll explain what they are in theory so that you can match them yourself later, but this is the most common terminology given to these. You split them up, and roughly, again, this is not a textbook definition, but roughly you aim for something like 80% of your data is training, 10% is validation, 10% is testing. Again, to each their own. This is a hyperparameter. Technically, you can choose, but this is a very common split that people will do. Why do you split it up this way? Well, remember the backpropagation, send a batch of data, calculate the loss function, perform backpropagation, do it again. You do all of that on the training data. So this is our gradient descent happens with our training data. It's only allowed to learn from the training data. Every so often every epoch, which is a term of art you'll want to know, epoch is a single pass of the training data. So you split up your training data into batches, and you do that backpropagation iteratively, that gradient descent iteratively. Eventually, you run out of training data. You get through all the training data that you had when you started. Once you do, that is called one epoch. So often researchers will define the length of their training in epochs. How many epochs, meaning how many passes of the training data are they going to do? Which, again, I'll hand wave away some caveats here, but caveat, if your training data is so huge, you could also just say less than 1 epoch, but again, that's not really common. Or you might say, well, go as much as 10 epochs, or as long as 10 epochs. But if you're on, let's say, epoch 2, and you're noticing that your model's not getting any better, then just stop. Don't waste my time with 8 more epochs. That's called an early stopping criteria. So how do you know if this is actually getting better as it's training? Well, that's where the validation data comes in. Every so often, usually, every epoch, you pause the accumulation of gradients. You literally tell PyTorch, stop accumulating gradients. We're not training anymore. You then test the model on the validation set, which is 10% of your original training data. It's never trained on it, ever. The model does not train on the validation data. It's effectively a pop quiz. The same pop quiz that you give it over and over and over again while you are training with every epoch. The reason you can give the same test over and over again is because, again, the validation set is never learned from. There is no gradient descent happening here. It's literally stop training, how are you doing? So you often end up with a graph that looks like a validation loss, which is often referred to as val loss. Sorry, that was the wrong axis to draw that on. You end up with a graph in which you have your validation loss as your y-axis and the number of epochs, or time, to be more precise, time on the bottom axis, the x-axis. And usually your first run will have a very high validation loss. Remember, lower is better. The next time you do it, we'll have a smaller one, and then you kind of notice it'll taper off after a while. And when you notice it starts to taper off, that's when you stop the training, or you just wait for it to complete with the number of epochs you set out with. Someone is asking a very good question about overfitting and underfitting. I'm going to answer it immediately just because it actually matches to what I was just talking about. The clearest sign of underfitting and overfitting, in fact, I believe there should be, hold on, let me check something here. In one of our, I think I have a visual of this in our code, so I just wanted to show it if possible. Yes, I think so. I'm going to zoom out a little bit here. Perfect. Yes. Let me share my screen here. So there's a lot of code examples in our GitHub, of course. Hold on. Still sharing. Here we go. In our GitHub, there is a notebook called Working with Pre-trained Models. VGG11 and BERT are 2 deep learning architectures. The architectures themselves are not the interesting part I want to show you, but it's a pretty long notebook in which I fine-tune, in this case, a VGG model to do image classification, specifically art classification of style of art. Now, remember I mentioned there's a training and validation. So what you often end up with is every epoch, you have your loss both at the training set and in the validation set. Here, I call it test loss. Again, verbosity might change from implementation to implementation. But here, my test loss is how I'm referring to my validation loss. What you notice is in a quote unquote the best case scenario, both of them go down together. As you are learning, you are keeping track of your error on the training data and the testing data. Now, you might be thinking to yourself, oh, okay, I understand the validation or testing data. You want that to get better over time. But why would you also look at the training loss? That's not the part we should be testing the model on. It's the part of the model we're training on, not the part of the model that we're testing on. And that's exactly the right intuition. However, it is useful to have in front of you, here's another example of both of them going down together. Again, a better loss is a lower loss, because you might end up with something like this. And this is actually talks about overfitting and underfitting in these as well. You might end up with something that looks like this. You go, whoa, this is really weird. Not only is my training loss going crazy, it goes down for a little bit and then jumps up for an epoch and jumps back down. You also have your validation loss, which I labeled differently here, going up, which is not what you want to see. Usually, when you see your validation loss starting to go back up, which is not uncommon. In fact, it is often very common that your validation loss will go down at first and then all of a sudden start to creep back up. When you see that U-shape going down then coming back up, that is a classic sign of overfitting, which the technical term is overfitting is when a model is over-learning the training data and losing its ability to generalize. It can no longer generalize to the validation set, which is a different data set that we're testing it on, but instead it's just memorizing and regurgitating the training data. So that's getting better, but the validation loss is not. So that's why we have both of these together. Because the interactions between them will give us a signal for how fine-tuning is going. So you do all this for several epochs, however many epochs you decide, again, at the hyperparameter. Like learning rate, the number of epochs, how long you do training for, is another hyperparameter, which people will guess. They'll say 10. They'll put in an early stopping criteria. Maybe 10's not enough. Again, you just don't know. Like, this is kind of the hard part of deep learning for a lot of people to kind of understand is, so it's a lot of guessing. Yes, it's a lot of guessing. It's a lot of educated guessing. It's It's a lot of guessing with decades of experience on what's worked and what hasn't worked, but it's a lot of guessing and checking. In fact, there are companies whose sole purpose is to help you keep track of all guesses that you're making. I'm pulling one up actually on the screen here. I'll share my screen one more time, sorry. Not one more time, but just for the sake of this example. There's a company called Weights and Biases. They sound familiar? They're an old company. They've been around for at least 10 years, I want to say. Like, I can't even remember exactly when they were founded, but they've been around for a while. Their whole claim to fame from a decade or so ago was why people rely on their system of record for training AI models and developing AI applications. They are quite literally their front page. No, stop talking to me. Their whole front page is, okay, great, initialize a project with us. Tell us your hyperparameters when you chose this many epochs, funny joke. And this learning rate, you log this metric, other funny joke here, you log this metric, or for a lot of people, loss, and then you say this was the model that yielded this specific metric. Because you're going to try different learning rates, different epochs. It's going to be a trial and error. And companies like Weights and Biases, which is a huge company, bought by CoreWeave, which is an even huger company, this company's only purpose in life is to help you keep track of all of those experiments, those parameters that you choose. Once you get a final model, you've done it for however many epochs, you've done whatever. Finally, you take that final model and you test it on the testing set. You don't do this until you basically tell yourself and the world, I'm done. This is the model. I'm now going to test this model on this final third data set and I will tell you what that number is so that you can see how good my model is. There's a name for these out in the wild. They're called benchmarks. Benchmarks are effectively testing sets that we all agree are good enough at the very least. And I can get into benchmarks a little bit. No, there's no time, but I can go off on a rant on benchmarks on the spot because there's a huge gap between benchmark performance and reality. But the definition of a benchmark is effectively a public open source testing set. So you, the researchers, do whatever you want. Use whatever training data you want within legal limits. Do whatever validation, testing split, do what you got to do. But we all agree that when you're done, you tell us you're done, you test it on this benchmark, like MMLU, Truthful QA, HLE, whatever, MLU, run it on this benchmark that I'm aware of, that Meta's also using, Google's also using, X is also using. They're all using the same testing set, the same benchmarks, so that we have some way of comparing models from different organizations to each other. So testing sets become more than just, is my model doing okay? They also become a marketing stunt to say, well, my model got better on this benchmark than that model, therefore mine is better. And it won't take you long to find people cheating by basically taking their benchmark testing set, putting it into their training set, which is a huge no-no, that's cheating. So the model actually has seen the answers to the questions before it is tested on them, which OpenAI has been caught doing. Meta has been caught doing this. I'm sure other people are doing it too. They just haven't been caught yet. But this is a real thing that people do to try to make their models better at a particular test set. Okay, we are at the top of the hour, and I want to take breaks as we go. And there's like 10 questions unanswered right now that I want to get to offline. So let's take our first break of the day. I know we're only 10 slides in, but it's a very, very comprehensive couple of slides before we get to our first bit of code. Then we'll start breezing through the slides a lot faster. So let's take our first break, 10 minutes. I'll answer some questions. I'll see you all in 10 minutes. Welcome back. I hope you enjoyed your silent disco. I've never heard that music before. It was very funny. When I turned the break on, I was like, what was that? I think we'll turn it off for future breaks, but I hope you enjoyed the vibes. I did. Anyways, okay, so deep learning. Got it? No, I mean, there's a lot more, obviously, to deep learning, but we got to move on into the practical applications of deep learning. And we'll start very simple with a technically complete neural network with a single layer and a single neuron doing the work of outputting, sorry, I should be clear, 2 layers, 1 neuron each. Sorry, I misspoke. 2 layers, 1 neuron each. We have this one here, FC2, or FC1, and FC2. F often stands for forward, because there's a forward pass and back propagation. Forward is how the data flows through the model. So an FC would be like a forward connector, or a feed forward layer is often how they are referred to in literature. In PyTorch, this is referred to as a linear layer. Now, why linear? Well, linear because if you remember from an hour ago, these are linear, I can't spell, oh my God, transformation. This is a linear transformation. So when we say linear, it's not like a linear regression or a line of best fit. They're specifically referring to the fact that this matrix is mapping of this size to this size. So if your data has an input size of, let's say, 12, your hidden layer, your one in the middle, might have something like 8, in which case you will need a 12 by 8 matrix to map your data to be from 12 dimensions to 8 dimensions. Now, if that's true, your final layer, maybe this is a classification algorithm where you only have 2 possible options, yes or no, and you want a probability for each one, like a 90% no, 10% yes. To go from 8 to these, you will need another matrix, 8 by 2. Notice, by no coincidence, that if you take these 2 matrices together, 12 by 8, and then which goes to 8 by 2, again, this is the effectively fundamental theorem of deep learning is, well, you multiply these matrices together, what do you get? You get something that approximates, why can't I type? Oh, that's weird. Anyways, I'll use my hand. My drawing is broken. Hold on, please hold. Here we go. You end up with an approximation from 12 by 8 to, you approximate a single function that goes from 12 to 2. This is the fundamental theorem of deep learning is we assume there exists no simple matrix that goes from 12 to 2. So to approximate it, we're going to go to 8, then we're going to go to 2. And by doing so, we hope we're giving the model enough room, enough parameters, enough memory, enough spaces to store all these learnings and their parameters to approximate this final map I want from 12 to 2. The only thing on here that I have not really spoken about too much is there's also something called an activation function, which I'm going to go ahead and call advanced deep learning, kind of 201. But very, very simply, more than just a weight matrix plus an optional bias, you also will pass these through an activation function, which basically will and someone used the term before, smooth the outputs, massage them to be a little bit more manageable. For example, common activation functions include a sigmoid, which will produce an output activation within a bound determined by the researcher. ReLU is a specific kind that is 0 all the way up till 0, and then linearly goes up after that. So you're basically just choosing the shape of the outputs of each neuron. Again, coming back to the idea that smoothing is not necessarily about making the model better by lowering the loss value. It's effectively a choice by the researcher that says, I think if we do this, we'll end up with better results. It's very much like a hyperparameter. You're choosing the architecture that you think will produce the best model. Okay, so how we classify the performance of a deep learning architecture is actually not on the deep learning architecture itself, but more around the actual task that you are performing. So whether it's accuracy for classification or mean squared error for something like regression, it has nothing to do with the actual model itself and more to do with the task that you are trying to perform with that deep learning model. Okay, so that was segment 1, our first roughly hour, in this case, hour, 10 minutes, break excluded. Now we can talk about the actual different experiment designs and loss functions that you'll generally encounter as you explore more of deep learning. I've already mentioned this actually, but companies exist who specifically help people do experiment tracking, like this is weights and biases, this screenshot right here. I'll be showing it in a few cases a little bit later on. We do this because, again, a lot of machine learning, deep learning included, as a subset of machine learning, is guess and check. Again, people will push back on me for that. Like, well, no, Sanad, it's experimentation. And I'm like, okay, but every experiment is a different guess, and you are checking the answer at the point is we're trying to pull it off of this pedestal where it's like you have to understand all this math or else it's not going to work for you. That's not really true, quite frankly. I'm giving you the bare bones of the math, but quite frankly, understanding more of the math will not necessarily make you better at working with deep learning models. It might make you better at making them, but geez, even I don't make deep learning models anymore. I simply take one of the thousands on the open market and fine tune it for my own purposes. Yes, sometimes I make my own deep learning models, but that, that's just my particular job. But most people do not need to do that. So when it comes to experiment tracking, one of those, again, hyperparameters is, well, what loss function are you going to choose? And as I mentioned, there are thousands, realistically hundreds, again, conservatively, that you can pick from. More conservatively, there's like about 20 that most researchers go for first to see if it works, and then expand into more complicated ones as they go. I'll tell you one right out of the gate. The most common loss function you will likely encounter is cross entropy, or CE. We'll see it in our code, our next coding example, our first coding example. Cross entropy. It is specifically a classification metric. Classification being defined as when a model is supposed to pick from one of a bunch of predefined options. Spoiler alert, GPT is a classification model. What? No, it's not, Saman. It's a generative text model. Not really. The fact that it outputs one token at a time is actually a good signal, because what the model is actually doing under the hood, and I'm going to give you a kind of a spoiler to some of our later slides here, which is when you talk about GPT, or what I'll later define as autoregressive language models, what happens is your input is all of your input text, and that text is massaged to fit into the deep learning architecture. But the output of the model is a classification of all the possible tokens, known as its vocabulary, that it can pick from. So if I say Istanbul is a great, what the model is literally doing under the hood is running a classification across, depending on the model, all 100,000 tokens on which one has the highest probability of being true. And then it is selected from that distribution what token will go next. When we say GPT and similar models are next token predictors, which is a common term of art you'll hear about these models, they're next token predictors because every single time you ask an AI to do something, a generative text model, it is predicting via classification, which is trained through cross entropy, what the next token should be. Now, if you're doing a regression type model in which you are predicting not from a list of options, but a raw number, like, for example, models exist which calculate the price of a stock in 1 hour, would be a regression model because you are predicting a number, not a class. You're not predicting up or down. You are predicting a specific number. Then your loss functions will change. There are loss functions that are created, and we'll see some in our documentation when I share my screen. Loss functions are formulas, but they are formulas with specific intent behind them. You choose a loss function that best matches both your task and your data. This is not an easy task. And again, most of these times, the frameworks that you use will choose this for you. I just call it out because, again, if you really want to get deeper into deep learning, one of the levers, the biggest lever that you have, is choosing the loss function. What defines error in my system? And can I choose the right definition of error, which best matches reality? So our first example is going to be a bit of a toy, again, but we'll get into the harder models after that. But just so you can see the inner workings of a deep learning model and how they are trained from nothing, we're going to train a classifier on a hello world data set of image processing called MINST. MINST is a bunch of handwritten digits, and we'll see them in just a moment. And I'm going to be doing it against a bunch of loss functions to see what the differences will be. Now, from here, from that MINST classification example, where we're going to make our own deep learning model, again, very simple one, I'll start to describe some common, let's say, subvariants of deep learning architectures, because deep learning is a big word. It includes a lot of different ways that people will cleverly construct their weights and biases, all with the same underlying premise that there are layers of calculation passing data from one layer to another, all trying to make an approximate of some large global function. So for example, in our case, our input is going to be an image, a single image. In our case, for MINST, it's a 28 by 28 pixel image. Obviously a very simple example. The end goal is to figure out what digit is this. Is it a 2? Is it a 3? Is it a 4? Now, models like Anthropic's Claude, GPT, Gemini, they can do this at a much larger scale, of course, but the same premise of the same basic backbone of, well, an image comes in, and then something that's not an image has to come out. So in this case, there's only 10 options. But if you think about Gemini or GPT, instead of 10 options, 0 through 9, there might be 100,000 options, one per token. Which token, the one that hopefully represents 2, should you say when you are given this image? So again, we know the answer. The AI doesn't know the answer yet until we could tell it how wrong it was and tell it to update itself. Now here, in all of the middle, we have what make a special kind of model called convolutional neural networks, or CNNs. Convolutional neural networks remain mostly state-of-the-art for all image processing models. So again, without going too deep, the main crux of a convolutional model is a convolutional layer, which is basically a way of taking, it's kind of hard to see on this, hopefully your PDF is should be more high def if you download it. It will look at particular patches of an image, meaning sets, like subsets of pixels, and it will basically use what's called a convolution, which is a way of mapping, it's a map, it's a weight matrix, mapping in this case, 5 by 5 pixel area into something that is a vector, which can be something that we can pass through even more weights and biases down the road. They're just special, clever and specifically built for images, transformations. But again, all of it can be described by microlinear transformations. Now, I'm going to breeze past this slide because this is effectively a history lesson. What used to be state-of-the-art in language modeling, and is still used to this day for non-language modeling time series tasks in particular, are called recurrent neural networks, in which the neural network actually has a recurrence, meaning it looks back on itself, meaning every time it predicts, it also looks back on what it predicted in the past for more information. So these used to be next token predictors until we basically invented a better architecture for language modeling in 2017, which I'll get to in just a moment. But for the sake of today, recurrent neural networks are not really used anymore. Even time series data is now being modeled by the same architecture that replaced RNNs for language modeling. So you just see it less and less these days. I bring it up only because they used to be a powerhouse. They still are talked about in some circles, so you might see their names come up. There's an example on the GitHub of training a larger convolutional neural network on image classification. We're going to do our simpler example on the MINT data set. Now, these slides, let me actually now get to our code demo here, and I'm going to come back to the slides after I share this demo. Okay, let me share my screen here. Share my entire screen here. Oh, good. All right, should be loading. I have both browser and my code here, which I am going to be showing my code in Cursor, which I love Cursor because I'll show you. It really helps me deal with my READMEs a little bit better. So Cursor really handles my README files for me to make them a little bit more readable, just because it's just harder for me. The code is easier for me than the actual README files are. Anyways, okay, so this in our GitHub, this is called First Steps with Deep Learning in MINT. As you can see here, we have many code files in our GitHub here. Like I said before, we're not going to get to all of them, but there's going to be a lot of examples and a lot of areas that you can look at if you want more. Okay, so in this example, and I'm going to walk through the code a little bit in detail here and move a little bit faster as more coding samples come up. But like I mentioned, a big part of deep learning is not just the theoretical, but it's also constructing the things themselves. Now, this is going to be an example of making our own deep learning model from effectively scratch, for which I'm going to use PyTorch, which is Torch here, and the requirements for this code can be found in the requirements.txt file here. Matplotlib for graphing. Torch Vision, which comes back to the concept of PyTorch having a lot of pre-built modules because it's been around for a while, big community. There is specifically a subset of PyTorch made for vision processing. In this case, it's called Torch Vision. Now, our data set is actually going to be downloaded directly from Torch Vision. You'll also notice here something called a random seed. Not necessary, but a very common technique people will do is one thing I didn't technically mention during the gradient descent, because there's so much to mention, but there is an element of randomness. I actually said this out loud, but there's a type of gradient descent called stochastic gradient descent. Stochastic is a very fancy word for random. So when we talk about stochastic gradient descent, there is a bit of randomness injected into the gradient descent process in a few ways, but the easiest way to think about it, every batch of data that you give to the model may be different if you randomly split your data into training, validation, testing every single time. So if you give it a different batch of data, it's going to learn a different step on that manifold, that loss manifold, and you're basically doing an entirely different training every single time. So what a lot of researchers will do is they'll set a random seed, which means they'll get the same random numbers every single time they run this code. That sounds very counterintuitive, I understand. It sounds why would you want the same random number? But what you want to affect your learning is not the randomness, your hyperparameters, your architecture, your data. Those are the things you can control, not the randomness of the batches. So if you set a random seed, you're basically telling your audience, from here on out, the things I'm actually setting are going to be reproducible. You'll get the same batches, you'll get the same everything. If you follow this code with my hyperparameters, you should get a roughly similar to what I got. It's not going to be exactly the same. Again, there's always going to be some randomness injected into the system, sometimes even from hardware. Long story short, GPUs actually have their own bit of randomness as well, based on how the hardware itself gradient. But again, so given that, setting a number, a random seed for reproducibility, good practice, technically not required. I also noticed that some people are asking questions about getting errors in running some of the code. I'm going to try to get to those during breaks, not during live time, just because there's a lot of people here. I don't want to spend too much time. Now, someone also asked during the break, and this is where it's relevant, how much does feature processing or feature engineering play a role these days? And I have written a whole book on feature engineering. Now, to be fair, I wrote that book before the rise of modern language models, and it's a little bit less relevant than it used to be 10 years ago. But back before deep learning was so popular, what humans had to do was create the features that the machine learning models would learn from. One of the big promises of deep learning is, well, it maps anything to anything, approximately. So if your earlier data, your input data, your raw data is actually, in fact, raw, deep learning will pick up the slack for you. it will learn the feature representations that you would have given to it if you had spent the time. That's the promise, I should be clear. That's not always the guarantee or the outcome, but that is the promise of deep learning. It will learn the feature representations so you don't have to massage it for the model. However, even still the case, and you'll actually see this in implementations of models that have image components. You'll have, for example, every time an image comes in, you have to convert it to a PyTorch tensor. You can also normalize the values of the pixels. This is very common, particularly with vision, where you have an image, but images could be of different dimensions, different formats, different whatever. So to standardize it, the researchers have to pick a format and then make sure that any image that comes in matches the format that they are expecting. And one thing that they'll do is that they'll normalize the pixel values so that they all fall within a certain range of values that the model was trained on to make the training more efficient. So what you see here is you basically say, we assume that this model will take all images and it will assume that the mean pixel value is this, the standard deviation is this, and then it will normalize using a z-score minus every pixel value minus the mean divided by the standard deviation so that they all live within a relative range of -3 to 3, like a z-score. Technically, it's not actually bound by -3 to 3, but normal data assumed that's the general range of data that you'll find it. They can go even further and say, well, images are roughly the same if you flip them around and remove some pixels and kind of manipulate it a little bit. So they can even say, well, I'm going to actually ruin the photo a little bit to make the problem harder. If you go to Hugging Face again, for example, and find any model that has images baked in, like this one, it's literally even called an image text-to-text model down here. Go to this one, go to Files, go to probably Config. Config has a bunch of information about the model. We're not going to get into today. Here's the activation function, CLU, not ReLU, but a sigmoid activation function here. Not ReLU, but CLU. Here's all the different types of layers that they have. Eventually, I think there should be, vision config. Okay, they have GELU, which is another activation function. PyTorch, hyperbolic tangent, a lot of math going on. I think they have, here, yeah, so for example, one thing that this model will assume is that there are 3 channels of pixels, meaning RGB values. There's a pixel for red, a pixel for green, a pixel for blue. Not all models will make this assumption. So this model basically has to say, if you're giving me an image that's like black and white, if you give me a black and white image, what the system will do without your knowledge is transform that image to have 3 RGB values, not just be in grayscale. So it's just basically a way for a researcher to say, look, I have to make some assumptions about these images that you're going to give me. And if you're going to give me something that does not match my assumption, I'm going to change it. Everyone does this. GPT does this. Claude does this. You just don't know what those are. Some models, anyways, let's move on. But that's to answer that person's question about feature engineering. So here's an image. It's a 5. Spoiler alert. So this is the model that we're going to use. This is exactly the model that I was showing you before so that we can get our models going. So in this case, we are going to have our input size of 10, for example, a hidden size of 4, and 2 classes. That's not going to be our exact sizes today, but I can make this model here, which, by the way, notice here how it is a subset of a neural network.module from PyTorch. If you look into the source code of virtually every single model on Hugging Face, they all subclass the same NN module. That basically, here's another one of them doing convolutional layer with a feed forward. So it's all the same, superclass rather. So we initialize the neural net itself using a superclass, the NN module. We just define the layers that we are going to have. So we have one going from an input size to our hidden size, from our hidden size to our number of classes that we are going to have. So similarly, like our 12 to 8, 8 to 2, this one goes from 10 to 4, and then from 4 to 2. And then our forward method defines how to use those layers. Our forward method takes in our raw data, passes it through our layers as we define them. So when we print out the model, it will look something like this. Now, to be clear, if we were to load up a model of another type, let's say, I think I do this in one of our later, one of these here. If I load up, not this one, but probably, where is, here. Hopefully, I just kind of print out one of these models that I looked at before. If not, I can rerun this code over the next break. I'll just rerun this over the break so I can show you what I mean. But when you print out a model, even like Qwen or BERT or GPT, it's going to look like this. It's going to show you kind of in order how these layers are being run. And you'll notice here, by the way, that it says bias equals true. As I've mentioned, that bias term, that bias vector, is also technically optional. I hope one of the things you're taking away from all of this is there is no singular correct way to create a deep learning model. The thing is, you always have choices. So the obvious question becomes, well, how do you know? You can't just guess and check everything. You're right. This is where the experience and the tribal knowledge really comes in. For example, adding a bias vector, again, in circles of deep learning, is becoming increasingly less common to include bias vectors in their models. The reason is because bias vectors are extremely helpful when your model is relatively small, because it adds a set of parameters that, again, picks up the slack of the linear transformations that captures the error of that particular microlinear transformation. But the theory will say that as the model gets bigger, you are allowing for more complex microlinear transformations. And with more data, the model can actually learn to fill in the space of those microlinear transformations. Therefore, we don't need this bias vector anymore. It's just added parameters that are not adding any value, but slow down speed of training and inference. So you end up with these empirical observations of deep learning models that lead to a global community level recommendation. So again, none of this is textbook. You do not use a bias when your number of parameters is greater than X. That's not how this works. It is very much a, look, from what I've read of people doing similar things, they tried it without the bias and it worked really well. But I think that if I add a bias, I can squeeze some more performance out of this model. I guess I'll try that. That's the experimentation of machine learning. Okay, so we can visualize our neural network. It's very pretty here. Let's get to our actual training here. So I'm going to define a few different loss options, and I actually have the documentation pulled up for all of these. We're not going to read them all because as you can already see, a lot of math goes into these loss functions. But no matter what the loss function is, you also have to define your optimizer. The optimizer, which as Cursor will or VS Code as well, will also very easily tell you, is that, okay, you could do things, different optimizers exist, like an atom optimizer or stochastic gradient descent is another one. So all of them are doing backpropagation. It's just slight variations in how atom versus, it wasn't showing up before, where atom versus stochastic gradient descent will do certain things. That being said, I want to say all, but I guess technically I've never seen all of them, but virtually all optimizers will have a sense of learning rate. That's that parameter I showed you on the slide about an hour ago. That learning rate will control how quickly we descend the loss manifold of our parameter vector space. So here's our model. We are going to have an input size of 784, which is 28 times 28, 1 neuron per pixel. Is this the right way to do that? Not necessarily. I mean, again, there is no such thing as a right way. There are ways that give you a better performance on the test set. That would be better, but I don't have a test set yet. I don't have any of this stuff yet. I'm making a choice. I'm designing this architecture to do 1 input per pixel, as opposed to be clear, a convolutional neural network, which before we run a convolutional layer, which takes a batch of pixels and converts it into a single number. So I'm making choices already by defining my learning rate, defining my optimizer. I haven't used my loss yet, but defining my loss, how many hidden layers should I have? All of these are now decisions that I have to make. And this is what researchers do day to day. They come up with a new architecture. They try to train it on the data. They look at their test set performance. They figure out what may have gone wrong, and they adjust everything and do the whole thing again. And weights and biases as an experiment tracking system helps them keep track of it all. So in real life, like after you are done listening to me rant today, in real life, you are never going to have to write this code here. This is all done for you by packages like transformers or TRL, which is a specifically created package for the act of fine tuning. However, under the hood of every single one of those optimizers, there is code like this that you just don't see. 10 years in my day, when I had to walk up a hill both ways to get to school, we had to write our own training loops like this. So these still exist. They've just been abstracted away. But I am going to show it to you so you can see what's happening. So to train a model, these are the basic steps that have to run. We give it our model, our loss function, our training data, the optimizer, and then how many epochs you want to go. In reality, there'd be a lot more to this, and this function would be a lot bigger, but this is the bare bones of what it takes to run our gradient descent. We put the model in training mode. What that literally means is that we're telling PyTorch, accumulate gradients for this model. Remember, accumulating gradients means we can perform backpropagation via the chain rule of our parameters. So I'm telling PyTorch to start remembering gradients. I log what time it is, so I can keep track of how long things take. For every epoch, meaning for every instance of the training data, we initialize a running loss for that epoch, which starts at 0. There is no error. 0 would, in theory, be perfect, a perfect model with no error whatsoever. For each image, for each batch of images, I should say, where I is the index of the batch, and then in the batch, we have our images and the correct labels. Again, we know what the right answer is. We know what's a 5 and what's a 2. This all presupposes that you have labeled data. I'll say thing here is, to be very clear, I'm also showing you, technically speaking, a subset of deep learning itself in which I do have the right answer in front of me, and I can use it to fine-tune this model. There's a name for that. It's called supervised learning, where I have the where I have the labeled data with the right answers in front of me. There are technically variants of machine learning that do not suppose that you have the right answers in front of you, but those models do not tend to be predictive. They tend to be more structural. For example, a lot of cluster algorithms, like k-means clustering, but they don't actually predict anything. Here, we are assuming that we are trying to predict something. There is to get to. So here, we have our labels. I reshape the image to the shape that I am expecting. And this training loader, by the way, which I think I glossed over, but initialized up here. This training loader is a PyTorch data loader, which means it'll give me batches of data from this data set of this size, batch size equals 4 in this case, shuffled around. So meaning it will shuffle the training data in place and give me batches from that training loader. And again, my random seed will ensure that when it shuffles the data around, I'll get the same batches every single time, which will automatically run these transformations, which will do this thing I described earlier. Why shuffle the training data? Long story short, you shuffle your training data for a very specific reason. The number one thing you do not want, the worst thing you could have, is a batch of training data that all look the same or very, very similar to one another. Because remember, this thing is gradient descending every single batch, more often than not. Every single batch of data, this model is back propagating. In fact, you can literally see it in the code here. For every batch of images, reshape it, run it through the model, we call this a forward pass, and get the final outputs. The final outputs of the final layer of a deep learning model are called logits. That's the raw number that comes out of the LLM. Oh, sorry, not the LLM, the deep learning model. And yes, LLMs as a subset of deep learning, but for any deep learning model, the name of the raw outputs of the final layer are called logits. You then massage those logits to be something more human readable, but the name of it is called logits. You take those logits and you compute the loss function. You compute the loss between the outputs of the model and the correct labels. So this number is our error. Then we zero out any of the gradients that were already being remembered, back propagate, and then step, meaning update the model's parameters given this backwards calculation, this backward propagation, the backprop. So we zero out the gradients that were being remembered. We then run the backward pass, run the step, and then keep track of the loss. I mean, we could have done this up here. We didn't have to do it all the way at the end, but keep track of the loss for the training value. And then we print along the way. So similarly, for evaluating the model, we put the model in eval mode, which will turn off the accumulation of gradients entirely, which saves time and memory. So we turn the model into inference mode. We keep track of our predictions. And then for the sake of to be very, very clear to PyTorch, we say, without calculating any gradients whatsoever in any capacity. So we're basically doing this in two ways. We're telling the model that there is no room for you to accumulate gradients. Then we tell PyTorch in general, do not calculate any gradients whatsoever, no matter what. Images in the testing loader, reshape the images, pass it through the model. Note there's nothing about gradients here. We see the highest predicted class, meaning the class with the highest logit value is the answer that it's giving. Add it to the true predicted label, add our real answers to the Y true, and then when we're done, we can calculate accuracy, F1, precision, recall, whatever it might be. So for these 4 loss functions, we are going to now train our model. Cross entropy, I actually have them here. Cross entropy, we have, in order of how I listed it here, we have the negative log likelihood loss, we have the multi-margin loss, and the KL divergent loss, or the Kullback-Leibler divergence loss. This is the point of the lecture where I have to tell you, 4 hours alone would not be enough to explain even the top 20 loss functions in enough sufficient detail that you truly understand the math behind them. What I can tell you, though, is that these are very commonly used loss metrics. Some, as I mentioned, cross entropy is the most commonly used loss function, particularly for classification, and KL divergence will actually be something that we see a little bit later, time permitting, in reinforcement learning. So I'll tell you up front that if you read the documentation for these two, they require a certain kind of output, specifically a log softmax output. Geez, what does that mean? It means that when you, let's see if I think they explain it in the docs. I'm trying to see if they have a, okay, not really. But if you, the are not what this model expects. This model, obtaining log probabilities in a neural network, is easily achieved by adding, I'm guessing this person's voice, is easily achieved by adding a log softmax layer in the last layer of your network. You may use cross entropy loss instead if you prefer not to add an extra layer. We did not add an extra layer. Our model stops at a feed forward. meaning there is no log softmax. If we wanted to add a log softmax, it would look something like log softmax. Well, yeah, there you go. And then in our forward pass, we would pass the output of the last layer through this. Now, log softmax is yet another transformation. It's not a linear transformation. What it will do is it will, to that other person's kind of question, smooth out the results. Oh, there's no images here. Wow, lame. Into something. Well, I'm just sharing my screen. It'll be a little easier. It would look like neither of those. Yeah, it'll look something like this. This is what a sigmoid or a softmax generally looks like. So the point is that we get, because I know our model does not behave well with NLL loss, the negative log likelihood, we may run into some problems. So let's see. Let's train the model for each of the loss values or loss functions. Here's cross entropy. And what we're looking at here, when it says loss here, we are specifically looking at the training loss, and then these are going to be done on the testing set. So we have our accuracy at the end, 97% accuracy, and pretty good F1 precision and recall, and we can see our loss value, particularly at least our training loss, going down over time, and our accuracy being pretty good at the end here. Everything looks like it is in order. If you did this with NLL loss, you'll notice that it didn't error. In fact, it didn't tell me that my model does not compute, basically, with this loss function. But it still doesn't error either. PyTorch is not going to really hold your hand a lot here. I'm telling you that this loss function was not a good choice. And you can kind of see that in the results here, where the loss function looks crazy, not something like cross-entropy loss, and the final accuracy scores are abysmal. It has effectively learned nothing. Now, if you run this code, each of these training cycles will only take like a minute or less on my CPU laptop, at least. But if this is a several hour, or in some cases in my books, several days long training processes, I don't want to wait for the end of the training process just to learn that it didn't work. So it is looking up if the loss that you are choosing, what you have to do to your model to make it work. Multi-margin loss, I know, does not have that problem. Multi-margin loss here seems to work roughly the same way. Notice the values are different, 0.2 here versus 0.03. That's not unexpected. In fact, because we're calculating error in different ways, we expect different numbers. So don't be alarmed that they're not the same numbers as cross-entropy. But this one seems to work pretty well. And KL loss, oops, we got an error. So in this case, it didn't really hold my hand, per se, but it failed because specifically, I mean, again, this is not a very helpful error, integral inputs are not supported, which is a very terrible error message. What's actually going on is that if you read the documentation for KL divergence, it expects log softmax, just like the NL loss does. And specifically, I don't think it's going to say it outright, but the KL divergence requires tensors of the same shape, meaning the output has to be a vector, like this. So instead of the label saying, oh, it's a 1, oh, it's an 8, oh, it's a 9, KL divergence requires that we give the answer in what's called a one-hot encoding, meaning it's zeros everywhere except for the class that is actually true. So this is a 1, and this is a 7, from 0 to 7. So instead of giving it as labels, 1 or 7, we would have to give it in this format. And again, this is just something you have to know about these loss functions, or else you'll just get errors, or worse, like an NLL, the wrong model, but the wrong model based on the wrong assumptions. So I update my training function a little bit to say, well, if we're doing a KL divergence or negative log likelihood, I need to do a log softmax of the final output. Fine. I have to do this to get the right loss functions. And also, if it's specifically KL, I also need to one-hot encode my results in the labels that I have. So then I get to run my models again, and with NLL and KL divergence, hey, look at that. All of a sudden, I'm getting the same numbers, or roughly the same numbers. I'm getting a pretty decent model. So to be clear, I changed my architecture 0. My architecture did not change, but my training code had to be updated to try a different loss function. Now, here's where I'm going to blow your mind a little bit. Mathematically speaking, cross entropy, negative log likelihood, and KL divergence are mathematically equivalent to one another in this example. I'm not going to get into why, I promise, but they are mathematically equivalent calculations. This is where I also show you that there is randomness in the system, even if you set a reproducible seed. You'll notice that the NLL loss technically got the best model given accuracy on the test set versus the other two. Not by much, but still technically different. It's a different model that is slightly better than the others. So even though it is the same exact mathematical calculation for this task, even though it's the same data, even though it's the same seed of randomness that we're setting, it's still slightly different answers. This is another fact of life with deep learning. is that even if you think you're doing everything exactly the same as you were before, you are going to get different numbers every time you run training code, guaranteed. Guaranteed. Until we make some major advancements in hardware, effective life for a lot of people. So I'm getting roughly the same answers because these are roughly the same, or exactly the same math calculations with roughly different training because the batches were different. The compute was a little different. It's just a little different. So one reason why I'm telling you it's the same for this particular case is that KL divergence is often used when the one hot encoding that you're given is not actually one hot, but more of a softer distribution. If you've ever heard of the term distillation, which in our last hour and a half of our time today, which we'll take a break in just a moment, in our last hour and a half, 2 hours, I'm going to be kind of doing a rapid fire of different examples and case studies. Distillation is on that list if we have time at the end. KL divergence is a big loss function in distillation where you are training a small model to mimic a larger teacher model. And it's also quite popular in reinforcement learning, and we'll see why. Okay, so this is our first kind of hello world example with deep learning, and it takes us pretty into our second break of the day, but there are a few questions here I want to get to. I'll do that one over the break. For the person getting an error with the models, you're on Windows. I'm not sure if that has another reason. If you want to copy and paste the error that you're getting specifically, you can, but into the Q&A. But I can look at it during the break. How many CTS? How many epochs are enough for a real world model? Very honestly, it'll range from finger in the air, 10 epochs to 30 epochs is a pretty sweet spot for a lot of people. Sometimes it can be more. Often it is not less if you are starting from scratch. Our examples after the break are going to have a lot fewer epochs because we're going to be doing a special type of fine-tuning called transfer learning, which I'll get into. One of the most important metrics, last question before our break, one of the most important metrics related to the models being more precise. Is accuracy the only one? Not at all. And again, not again, but we're not going to have time to get into all of the different metrics. I have a whole 4-hour lecture on evaluating models where I do a deeper dive into these different metrics. But accuracy is by far not the only metric that you should be using to evaluate a deep learning model. And that will depend on the task itself, again, not the architecture. So if you're doing classification, you have precision, you have recall. There was an O'Reilly kind of mini conference the other day in which we talked about how CodeRabbit, one of the world's largest code reviewer, looks at precision and recall of their AI, meaning of all the times the AI made a change, how often was that change right? That's precision. Of all the times we expected the AI to make a change, how often did it do it? That's called recall. So depending on what exactly matters the most to you for a specific task, that's going to define the metric that you use for the entire. But that's outside of deep learning. That's just AI in general, and deep learning is a subset of AI. So yes, those metrics matter, but it's not a deep learning specific calculation. Okay, another break. Let's take a 10-minute break. We're about halfway, a little over halfway done. When we come back, we're going to dive into more fine-tuning of deep learning models, and specifically fine-tuning of pre-trained models, i.e. models off the shelf. But before we get into any of that, we're going to have to get into a mini lesson on language models as a subset of deep learning. So I'll see you all in 10 minutes. All right, welcome back. Apparently, we did not fix the the vibes, but I hope you like the music. All right, moving on. to our next segment, talking about LLMs. Finally, am I right? Well, because here's the thing: LLMs are a subset of deep learning in most cases, and the history of deep learning in language modeling actually goes back to 2001, with a few advancements along the way. I get more into these in another lecture of mine, but more specifically, culminating in a 2017 discovery of a new type of language model. So the first language models with deep learning 25 years ago had the same task that they have today, which is this is an image from that paper in 2001, in which you had tokens coming in, like raw text, and then the thing you are trying to predict is what token comes next, given the term context. So we talk about context windows, context engineering. That's a 25-year-old term for language modeling in deep learning. And you can see here we have these, feed forward layers. Hyperbolic tangent is a type of activation function. A softmax at the end turns things into probability. These are effectively all the same concepts that we've been talking about. Now, in 2017, a new deep learning architecture based specifically on a type of math calculation called attention came out. That architecture is called the transformer. It's the T in GPT. It's the T in BERT, which maybe you've never heard of. It's the T in T5, which is another one you've maybe never heard of. So what is language modeling anyway? What's the task that we are trying to solve? In a long story short, language modeling is about filling in the blank. If I give you a sentence and I give you a blank in that sentence, the task is what token, or word, but token is more precise, what token goes in that blank? And that token will come with a probability, a chance that it is that token, because many words may actually fit. Stop makes sense, yield makes sense, but stop is more likely because there are just more stop signs out in the world. So it's just statistically more likely that the word is going to be stop and not yield. Now, really, there's actually two main types of language modeling you need to be aware of. There's autoregressive and autoencoding. And the difference is where that blank is allowed to be. What I showed you is an autoencoding language modeling task. The blank was in the middle of the sentence, which is the defining feature of autoencoding language modeling. Autoregressive language modeling means that you can only have a blank at the end of the sequence. You are not allowed to have context that go into the future. You can only look backwards for context. And this is because in real life, when the AI is speaking, it doesn't know what it's going to say in 20 tokens. So it's cheating to teach it. It's coming back to that idea of cheating with training data. You can't cheat the training of an autoregressive language model by giving it future tokens. Question: what research paper introduced the attention computation? That's a really good question. I don't know which one introduced I don't know. I won't lie to you. I don't know the exact first time that the attention calculation was used. I do have a few here of early instances of it being used in 2014, but I can't tell you specifically if that was the first time the attention mechanism was used. I will actually look into that. I'm curious myself. So we have many language models out there, like BERT, the bidirectional, because it's an auto-encoding language model, encoder, which is a part of the transformer architecture, representation from transformer, originally invented in 2018, remains to this day, on April 23rd of 2026. It is the second most downloaded model on Hugging Face in the last month, not of all time. In the last month alone, BERT, a model created in 2018, a deep learning transformer-based model, was downloaded tens of millions of times, more than Quen, more than Kimi, more than any other open source model, save for one or two. So even older language models still find new life today. Now, for the sake of time, I'm going to skip over the pre-training of BERT, but I will point out that the pre-training of BERT is effectively classification. All language modeling, as performed by transformer architectures in a deep learning capacity, is classification. In fact, when you talk about what token belongs in a certain spot, that's a classification task in which we ask the LLM to pick from its vocabulary of all possible tokens. GPT, the generative pre-trained transformer. Generative, because it's autoregressive, pre-trained, as we'll talk more about pre-training a little bit later, basically meaning it was already trained on data before we downloaded it or used it, and T based on the transformer. In fact, the first GPT was in 2018, and we've had many releases, of course, since then. Not talking about the most recent releases, because I'm assuming you are more up to date on that, but the first GPT models were actually in 2018 with only 117 million parameters. Now we are in the trillions of parameters. So even in the last 8 years, these models have gotten way bigger than anyone has ever been able to deal with in past iterations. GPT itself was also trained on data. Again, for the sake of time, I will skip that. But I will also show you, like BERT, where it's asked to fill in the blank. As I mentioned before, this is a classification task. Of all the tokens in its vocabulary, which is still a lot of tokens, hundreds of thousands for modern frontier AIs, which have to encapsulate English, different languages, punctuation, misspellings in certain scenarios, numbers, all of the things that emojis have their own tokens, all of these go into the vocabulary. So whenever a generative AI model speaks to you, it's basically performing classification very quickly in succession. Open source models exist as well, or open weight models, if I'm going to be more precise in my terminology. More famously, the large language model from Meta AI, or Llama, exists. But since then, we've had Qwen, Kimi, Mistral, Gemma. There are so many different open models that people are using these days. Llama just happens to be first, and therefore kind of paves the way for how popular open weight models could really be. Meta used to, at the very least, publish their training regimen with not everything being open, but it really highlights that the training recipes that we've settled on in the last couple of years have kind of plateaued. So OpenAI popularized a 3-part training regimen, which basically means that when you train a model, you don't just do like our Mint data set. You don't just do the fine tuning once on one data set. You actually split it up into usually 3 different components. First one is called pre-training. And that's when you take a blob of data, you remove the token at the end, and you say, what token goes at the end? So this is called a semi-supervised task, because a human did not label the answers here. Instead, you just take Wikipedia, take a paragraph from Wikipedia, remove the final token, and ask the model, what do you think it was? And then the model says, I think it was going to be blank. But you know what the right answer was, because you started with it, you just removed the token yourself. So you now have a model prediction, you have a ground truth, which is ground truth from the internet. You compare them, get a loss function, do back propagation, the rest is history. It's all the same deep learning. You choose your architecture, you choose your data, you choose your loss functions, you choose your hyperparameters, everything is done for you in PyTorch and TensorFlow. Second stage is called supervised fine-tuning. I mentioned this term before. This is where you give the model human label, or often synthetically labeled these days, but usually human labeled data. Usually things like, this is a back and forth conversation between a human and an AI that I want you to emulate. The task is still the same. I'm going to remove certain tokens and ask you to fill in the blank. It's just that the difference is, instead of just taking a random paragraph from Wikipedia, now I'm giving you a human curated conversation in which you should be emulating. The last part of the training, they're calling it here human preferences, but in reality, this is where reinforcement learning comes in. And if there's time at the end, we will talk a little bit about reinforcement learning, but I have a whole 4-hour lecture just on reinforcement learning and a longer video series on O'Reilly if you care specifically about that branch of deep learning. But most of the training being done, data-wise, trillions of tokens, hundreds of thousands of examples, are done on the first 2 phases of the training, which directly map to the loss calculation backpropagation that we've been talking about. It's not that reinforcement learning doesn't rely on backpropagation. It does in deep learning, but there's slightly more to it, which again, if you have time at the end, we'll get to. So yada yada. There are 3 main ways in which we can use a language model. We can either use them to embed data, like using an embedder. We can prompt them, which again, this is not a prompting class, but you can prompt them to do stuff. Or we can fine tune the actual deep learning architecture in order to get a different model with different parameter values for a task that we are actually trying to solve. So the reason I call this out here is we call this process transfer learning. Transfer learning is a theory, technically, in which if you have multiple stages of fine-tuning for a deep learning model, information learnings transfer from one stage to another. So coming back to this llama diagram, for example, by letting it read Wikipedia, for example, during its pre-training on a semi-supervised task, you're basically hoping that knowledge from Wikipedia transfers over to supervised fine-tuning. So when I teach it how to be a chatbot, it will also have knowledge from Wikipedia. Now, I'm saying Wikipedia as a placeholder for a large corpus of the open internet, but the idea being that information lives in the pre-training phase. Most of what an AI learns is in the pre-training phase, in the autoregressive language modeling task, which is just classification, which, do you want to guess what the loss function that they use for token classification? I'll give you a minute to guess while I take a sip of water. That's right, it's cross-entropy. They use OpenAI, Frontier AI, uses the same loss function we just used on our Mint data set. What's the difference? Bigger model, bigger data sets, bigger budgets, quite frankly. There's a lot more, obviously, but those are the main 3 things that are different when it comes to what OpenAI is doing. No one doesn't know what the process in which OpenAI is taking to make their models. Yes, we're guessing because, again, researchers have their, they have their little levers that they can pull. But for the most part, it's not like they're not using a deep learning transformer architecture or backpropagation or gradient descent. It's not like we know they're doing that. It's just, well, what data specifically are they putting into their models? That's the part that we know less of. Okay, so transfer learning at a higher level will look like taking a model off the shelf, piping in custom data for your task, and potentially altering the deep learning architecture by usually adding on top of it. And this is something that even big companies like eBay will do. eBay took a BERT model, yes, the same one from 2018, fine-tuned it on their historical recommendation data so that when you looked at an item like this Michael Jordan baseball card, you would get a bunch of similar items. Like, oh, you like this? You might also like these. when they trained an LLM on a specific task. This is not language generation, but their specific task was predict the next item that they might want to look at. Then they were able to show increases in revenue across all of their platforms, like mobile and non-mobile platforms. That's a pretty big deal. So large companies will fine-tune data with additional task layers for their specific task. Now, of course, if you don't want to train your own model, you just want to use like playgrounds and APIs, you're welcome to. Okay, so when it comes to the types of language models, mostly auto-encoding versus auto-regressive, the basic breakdown is autoregressive models are for when you say the term generative AI, that itself is a bit of a misnomer because it's specifically referring to models that generate data. But BERT does not generate anything. BERT is an auto-encoding model. It doesn't know how to speak. Auto-encoding models are non-generative large language models, but they are built on the exact same deep learning architecture, the transformer, like Claude, Gemini, DeepSeek, Mistral, whatever. Combination models, both auto-encoding and autoregressive models, exist. They're not very commonly used outside of multimodal applications, which again, time permitting, we'll get to. So case study and fine-tuning is one on classification. So we talked about this before, the process of fine-tuning, so we don't have to do that again. Here's our data set in this example, and I'll show code to do this as well. Here's our data is going to be, the input is going to be a review of an app, and the output is going to be how many stars did this person give. So this is a 5-star rating. This would be a 1-star rating. Now, this might sound like a very simple task, and in a lot of ways it is. But as a consultant and having worked for companies as big as Adobe and as small as 10-person companies just out of an incubator, almost all of these companies at one point have written a prompt that forces GPT or Claude to pick from a set of options, and that's the only thing it's doing. It's a prompt that basically says, of these 5 options, what option does this one fall under? That's called classification. And if you don't want to do that with a prompt, and you would rather do it with something cheaper and faster, you could fine-tune a classification model like BERT. So a couple more hand-waving things, like again, for the sake of time, I have to just say, all language models have special tokens, meaning tokens that researchers put into the model in order to teach the model structure. For example, chatbot LLMs, generative models, have special tokens that tell the AI when the human is speaking versus when the AI is speaking versus what's a system prompt, what's a developer prompt, what's a tool message, all of the different capabilities that researchers attempt to put into a generative LLM. Special tokens tell the LLM what structure that chat will take. In a BERT model, which is a non-generative, non-chatbot LLM, there are still special tokens, but specifically, there's a token for classification. So Google, who made BERT, Google researchers put a CLS token in the model so that we, consumers of BERT, can fine-tune on top of it using a feed-forward layer, which we'll see in a moment, to classify whatever it is that we're trying to do. Now, we're going to compare this to fine-tuning a GPT model to also do classification, which is something that OpenAI claims they could do on their documentation. Here's the problem. They're lying. That's a big statement. I'm not saying, oh, God, they're the devil. But they're kind of lying a little bit because it's not definitionally speaking classification, meaning it's token classification, meaning you are picking from the model's vocabulary. But for example, in our example, where we are giving only 5 options, there's only 5 options here. When you train a GPT model, it doesn't only pick from those 5 options. You're basically tuning the parameters, but it still is a classification of all of the 10,000, 100,000, however many items are in its vocabulary. In fact, in the code, you'll even see this very clearly in that sometimes when I use my fine-tuned model for classification, it outputs something not from one of those 5 options. And yes, you can add more to fix that, band-aid it. But the reason I bring this up is you have to be aware that when a company comes at you and says, oh yeah, do classification with us, you have to be kind of more, we, the consumers, have to come into that bargain with some AI literacy, saying, well, it's not technically classification on my classes. It's classification, legally speaking, it's classification on GPT's vocabulary set, of which my options fall under that category. But they won't guarantee that the model will only spit out the 5 options I care about. However, in our auto-encoding model, which is an updated version of BERT called Modern BERT, which came out about 1.5 years ago, almost 2 years ago, at the end of this year, it will only be able to output classes of those 5 that I mentioned previously, because we're adding a layer on top of that open model to do so. GPT is not an open source model. We cannot alter its architecture. We can only band-aid on outside of the model things like, oh, if you didn't output one of my options, redo it or do something else. But you cannot change the architecture of GPT. Okay, let's actually look at the fine-tuning code for BERT before we get onto our results, which I'll show in just a moment. So on the GitHub, we are looking at here fine-tuning BERT versus GPT. The first one is a Colab notebook, mostly because it's going to be I did use a GPU to do this fine tuning. You don't need a GPU. It's small enough that you can get away without using one, but it does speed things up quite a bit. So I'm going to go a little bit faster just for the sake of A, time, and B, there's more code here, but I want to walk through the broad strokes of what's happening. Instead of using raw PyTorch, I'm going to use the transformers package, which is built and maintained by Hugging Face, which defaults to PyTorch under the hood. Note, I'm still setting a random seed here, just like before, setting up the data into a 75-15-15 split for training, validation, and testing. Note, specifically, before I do that split, I do something called stratification, especially in imbalanced data sets. For example, if you are trying to build a classification model where you have one class that is way more represented than others, a stratification is a very handy technique. Now, I can tell you that this specific data set, which we can actually look at in, here, in Hugging Face, if you look at the star labels here, you can see that the 5-star ratings are actually represented. 60% of the data is a 5-star rating. 4.6% is a 2-star rating. So this is a pretty imbalanced data set. Now, even if you have a balanced data set, it's almost never, it's not almost never, it's never a bad thing to stratify your data splits based on a certain category. Just so, and again, the point is, you want representative data. Your data, your training data in particular, should mimic what the population, the real distribution looks like as much as possible. So we do this, we split it up. We have hundreds of thousands of examples here. I have my modern BERT. Language models also do have a pre-processing step called tokenization. So again, feature engineering is not really something people do anymore, but there still is pre-processing. So in the MINT data set, remember, we had to turn our images into tensors, and then also additionally, we z-scored the pixel values based on a given mean and standard deviation. Here, we have to take in raw text and split that raw text up into indivisible units of language we call tokens, which I'm not going to, again, for the sake of time, I'll hand wave away. But what you end up with is when, and I have classes specifically dedicated to the transformer, which again, we can talk more about in those. But here the idea is you input an input, like nice with a winky face. And then this is the actual input the model will see. A special token, CLS, a token for nice, 40194, or sorry, that's Sinon. A token for nice, a token for winky face, and then the SEP token, which is another special. So these CLS and SEP tokens are two special tokens in BERT. So we tokenize all of our reviews. We then end up with a dataset dictionary, which is a class in the transformers package. And the things we care about are input IDs and label. Input IDs are the raw tokens, which are going to get passed into the model. And then label represents 1, 2, 3, 4, or 5 stars, which will be 0 index, 0, 1, 2, 3, or 4. Now, also hand waving away, there is another step between tokenization and when it enters the model called embedding. But again, for the sake of time, we're not going to be able to talk about the intricacies of every deep learning architecture that we talk about today, so we're going to move on. Now, what's nice about transformers is you can actually load up most of their LLMs for a specific task. So in this case, I'm going to load up an auto model for sequence classification. And what that actually does, and I think I have a local, oh shoot, I deleted it, sorry. What actually happens here, and in fact, maybe I can run this hopefully pretty quickly. It died during the break, I feel bad. I ran it and then it died. If I can run this, I can actually get our what the model actually looks like, so I can show you. So let me run the particular code cells that are going to be relevant here, and then hopefully within a minute or two, we can actually see this. Because what I want to show is when you load up this model for sequence classification, it will automatically add the additional task layers on top of the CLS token to perform classification. Meaning it will add a feed-forward layer that maps to the specific number of classes that we are looking for. A question coming in, by the way, from AB, is there seems to be a different transformers package, one of which is from Hugging Face. What are the other ones from? There seems to be a different transformer package. It's the one from Hugging Face. If there's another one not from Hugging Face, that's not the one you want to use. You want to use the transformer package. It's just called transformers. So if you install transformers, and then here specifically I'm noting it for PyTorch, it should work. So here it's doing the imports already. So it's installed everything. Come on, import things faster. Initial imports are always a little slow. Anyways, while this is going, we will have a helper function here to calculate accuracy. And then here is our training loop. Note, it's not actually writing the for epoch in epochs, do the data loader, do this, backpropagate. That's happening under the hood. But we don't have to look at that here. All we have to do is set our training arguments where we have things like how many epochs. Here I just do one epoch. How many things in your batch size. I have some other hyperparameters I'm allowed to choose. For example, here we go, perfect. Okay, it's done. So when I load up this auto model for sequence classification, what it's doing is it adds these layers at the end here. Meaning all of this, let me zoom out a second, all of this model all of this is what I downloaded from Hugging Face. These layers, most notably this linear layer, exactly the same linear layer we saw in our minced classification, maps from 1024, which happens to be the output of the model's final layer here, 1024, and maps it to, you guessed it, 5 things, 1, 2, 3, 4, 5 stars. And that's the parameter that we put into the sequence classification up here of number of labels equals 5. So it adds these layers and also very specifically tells me, hey, by the way, the weights here are missing, meaning they were newly initialized and missing from the checkpoint that you downloaded. Consider training on your downstream task we're about to do. It also says that this decoder bias is unexpected. This is a bug in transformers, and you can be ignored. We are ignoring this, but this is the thing that is missing because we haven't fine-tuned this yet. And note, there's a weight and a bias. So it adds these parameters on my simulation. Will actually wait to do backpropagation for a number of batches. In this case, I'm setting it to 16, mostly because I can effectively have larger batch sizes without having to use more memory. So gradient accumulation steps is a hack to basically simulate larger batches with less memory. Batch size for eval, which can be larger, 128, because there's no gradient accumulation during evaluation, so I can increase my batch size. Load the best model at the end, meaning it will keep track of the value loss and only load the model along the way with the best value loss. And then I have some other hyperparameters. I have some other logging parameters. My trainer takes in the model, the arguments set up here, the training data, the validation data. I have an optional method here to calculate accuracy because it's not automatic. And then I also have another thing to speed up the training called data collation or data with padding, which there's a slide for, but I won't get into. Before I do any training, if I run .evaluate, I can get a preliminary loss value and an accuracy, 20% accuracy, a 1.7 loss. And by the way, in case you're wondering, the loss function that it's using by default is cross entropy because it's classification. When I hit .train, I can follow along each epoch. I only did one epoch. By the end, we have a training loss, a validation loss, and an accuracy. So if I run, if I compare this to before, the validation loss dropped from 1.7 to 0.7. Accuracy climbed from 21% to 73%. But remember, this is not the number we want to report. There's a test set. That's the validation accuracy and loss. I also want the loss for the test set. So I can pass into the .evaluate method the test function, which will be minutes to go through the entire test set. Still a long time. It took, for what it's worth, it took 2.5 hours on a GPU to fine-tune this model. 2.5 hours for one epoch. This is a 200 million parameter model, like hundreds of millions, or it's not even billions, but to train it for one epoch on a GPU took hours. To give you a sense of scale here, like for the same amount of data on a larger model, one epoch might take 24 hours, not 2 hours. So when I say weeks or months to train a model, I'm not kidding. Like this scales very, very quickly. So I run it on my test set and I get an accuracy of 73%, which is luckily similar to the validation accuracy. Very, very similar. That's a good sign. And the loss is also very similar as well. I can push that to Hugging Face, which I have. You can find it here if you want. And then I can use it. I can actually run it. Oops, I forgot to run this whole thing here. But I can then run it against to get different metrics, in which I will stop sharing my screen to show the results. Now, also in the GitHub, there is a notebook on the actual fine-tuning with OpenAI. So you can see how I use the API to actually do the same work on GPT 4.1 and 4.1 Nano on the same data. But I'll stop sharing my screen so I can actually show you the results of it, not just the code. So results-wise, we have top-line accuracy on the test sets. I already showed you for modern BERT, it was 73%, but GPT 4.1 and 4.1 Nano also got roughly 73%. So given the data, this huger model didn't really seem to make much of a difference. And that's going to be a pretty big thing that you'll have to know in deep learning. Just because the model is bigger and better and trained with more data does not necessarily mean it will actually do better on your task. If your task is something as quote unquote simple as classification, you are honestly, a lot better off picking a smaller model like BERT for the sake of some other characteristics that BERT has. I'm going to come back to these curves in a moment if there is time. But more kind of at a high level, it cost me $1 on Colab to fine-tune modern BERT and $122 to fine-tune GPT 4.1. Again, just to get roughly the same accuracy. At inference time, modern BERT is roughly the same cost as GPT 4.1 Nano, but GPT 4.1 cost a lot more. So why would I pay more money to run, more money to train, just to get basically the same accuracy? Great question. Now, you could argue that, well, by doing it with a generative model, if the classification changes, I only have to simply change the prompt. I don't have to refine-tune the model. And that's fair. But for a lot of people, their classification doesn't change. If they only had 5 classes last week, it's not going to be 7 classes next week. A common example that people come to me to help them fine-tune is something like Salesforce fields. Well, they'll say, we need to backfill all of the Salesforce data. There's only 49 options, and there's not going to be more or less. So train a model to pick from one of these 49 options as quickly as possible so we can backfill these hundreds of millions of rows for this project. So it's not always that, oh, we're building a new feature, we need it to change every so often. Sometimes it's a backfilling operation, which is boring, but there's budgets of millions of dollars to get this done. So picking the right architecture is going to matter. And if you have a sense that the type of task that you're doing, like classification, is a, again, relatively simple task, you might as well train a cheaper, also faster model, because the BERT model is also going to be faster at fine-tuning, given that it's, I mean, among other things, extremely small in comparison. Now, I am going to take a break in just a moment, and then we'll come back off our examples for the day. We'll talk about chat fine-tuning, which someone asked about for something like Llama Guard for guarding against unwanted inputs and reinforcement learning. But before I take a break, a very, very brief mention of calibration. You'll see this term a lot. Calibration at a high level is the measurement of a model's prediction confidence to reality. In a classification sense, it is quite literally the difference between the predicted probability of something happening and the actual probability of something happening. Said another way, if a model predicts there is a 70% chance of something happening, then we can compare that to the actual percentage of that thing happening. So here, for these different curves, so what you're looking at is called a calibration curve. Each graph represents a model and a technique. So here's GPT Nano with no prompting whatsoever. When it predicts for the red and purple, which is class 3 and class 4, meaning 4 and 5 stars, let's focus just on purple, which is a 5-star rating. So for the 5-star rating purple curve, when the model predicted 70% confidence of it being a 5-star rating, of all the times it said, I'm 70% confident that it's a 5-star rating, in reality, only 50% of those were a 5-star rating. So the model was overconfident in what it was predicting. In fact, I'm looking at the documentation right now for one of our losses, and they specifically call out when certain losses are more useful when you are trying to get more calibrated, meaning more softer probabilities in line. Now, this graph here, these 4 graphs rather, represent 4.1 nano, 4.1 nano with a system prompt, 4.1, and modern BERT. Each of these are calibration curves. I show them because BERT actually has the better calibration, even though it has a better calibration and a lower accuracy than GPT 4.1, meaning it's not willing to generate predictions for which it is neither over or underconfident. It is only willing to make predictions that match what it thinks is reality. GPT, as you can kind of see one of these curves as an example, is willing to predict things that it is not confident about. It happened to be right in some of those cases, which is how it got a better accuracy, but it's by guessing. BERT is unwilling to give predictions for which it is not confident. So the choice of architecture also impacts a sense of calibration. So when you see people talking about calibration, underconfidence, overconfidence, it's a data question, it's an architecture question, but it's also a training regimen question. Okay, we're gonna take one more break for the day, just a 5-minute break this time. When we come back, we're going to keep going with our next case study on fine-tuning for chat data, and then we'll keep going from there. So I'll see you all in only 5 minutes. right, welcome back. That was going to be the last break of the day. We have about 50 minutes left. And in that time, we're going to go through some more case studies. I'm going to keep those questions coming, please. I no more. I've answered all questions offline, or the rest of them that I saw. But please keep them coming. Okay, so next example is about chat fine-tuning, which is going to, again, look very similar to what we've been doing before. It's next token classification. Now, the motivation for talking about chat classification really goes all the way back to OpenAI's alignment work back in 2022, in which they taught their GPT-3 model to produce a more chat-like output. So this is kind of considered to a lot of people the kind of proto chat GPT, because it was basically a single input-output, but that was expanded to be multiple turns back and forth. So this is actually an example that I do in one of my textbooks, a quick start guide to large language models, if you want to see the full case study that I do there. But basically, it's broken down into a few steps. Step one is I train an LLM off the shelf to follow instructions, to follow a conversation. Next, I train a separate LLM on a task to detect when a chatbot is speaking well or not, like in a way that a human would prefer or not. Third step is I use what's called reinforcement learning to update the model even further to be more in line with my human expectations. So we're going to go through first step one, and then if there's time at the end, we'll come back to steps 2 and 3. So step 1 is teaching a model to hold a conversation. Now, if you are not aware, many AI providers, like Google is a good example of this, and Meta does this too, or did this. They haven't put out a model in many years. When they put out a chatbot model, they almost always also put out what they call the base version of that model versus the instruct version of that model. If you look at Gemma 4, which is an open source model, open weight model, from Google, at the end of the model name, it says IT. IT does not stand for Italian. No. It's also not your IT department. No. It stands, why is this pen breaking all the time? Shoot. Clear. Okay. It stands for instruct. So you have to give the AI examples of conversational data so that your model goes from this, which is what happens after pre-training. So this is pre-train only. A model will look like this. You ask a question and you get back an answer that is not really an answer. It's basically just pretending this is an article on the open internet. It has not yet learned your special tokens, your structure, your conversation. A human versus an AI speaking, what does that mean? It's just regurgitating stuff from the open internet. Once you go through the supervised fine-tuning process in which you give it curated conversational examples, then you can ask it a question and it will actually give back an answer. Now, I'll show you the code in just a moment. I'll also walk through some of the deep learning fine-tuning tricks that we use in the real world. One of the most common, and I would argue this is a top 5 advancement in AI in the last 10 years, because this works for any deep learning model, not just language models, is called LoRA, low rank adaptation, which is itself a subset of a family of techniques called PEFT, parameter efficient fine-tuning. I'll give you the long story short. When you are training a model, you have weight matrices. Remember those? These weight matrices weight matrices are parameters. They're rectangular matrices of numbers. The long story short of what LoRA does is it does something called matrix decomposition. In linear algebra, what that basically means is you split up a single matrix into a multiplication of several matrices. So the weight matrix basically becomes another smaller matrix times another smaller matrix. Here's the trick. If you assume what's called a low rank, which in linear algebra world, that means that your weight matrix has too many dimensions that are required to represent the transformation it is representing. So a weight matrix represents the transformation. A low rank assumption assumes that your weight matrix is actually too big for what it is trying to accomplish. You only required fewer parameters. If you make that assumption, you can decompose the weight matrix into smaller sub-matrices and then basically fine-tune those smaller matrices, and it's as if you fine-tuned the bigger one. I know that sounds magical almost, and it is, but it's actually called linear algebra. And the paper is quite fascinating. Oh, shoot, I don't link it here, but if you Google LoRA paper, you'll find it very quickly. It's a trick of fine-tuning a model with smaller matrices. The second trick, just for the sake of speed, I will go through the third trick, which is more common in most cases, called completion-only loss, or sometimes referred to as assistant-only loss. Generally, when you give the AI a string of text, which includes multiple turns of conversation, here's the human speaking, here's the bot speaking. You don't care if the AI incorrectly guesses what the human says. You do care if the AI incorrectly guesses what the bot was supposed to say. So when you give the AI a curated conversation, what a completion-only loss or an assistant-only loss says is instead of calculating the loss using the entire input, meaning human plus bot messages together, only calculate the loss based on what the bot tokens were. If the AI guessed wrong what the human said, who cares? Who cares? Seriously. I only care if you guessed this part wrong anyways. So you're basically, it's the same loss calculation. You're just only calculating it when you take away tokens from the bot side. By doing so, you basically direct the AI's training only on predicting the bot stuff and not on the ancillary stuff, like predicting what the human would say. So let me share my screen to show what part of that code will. Here we go. All right, we are looking at fine-tuning Llama 3 to be a chatbot, which will open this collab notebook, which I'll be very honest with you. In modern days, like today, I could rewrite this entire notebook in about, with 75% less code using other packages that abstract away a lot of the work. But again, for the sake of education, this notebook tries to show with as much detail as possible the inner workings of what's actually happening so that you can at least see it. So the data set I use for training is called Guanaco, a not so state-of-the-art anymore, but still a very large, comprehensive, conversational data set in which we have a human saying something and then an assistant saying something. And it goes back and forth in this format. So if we parse the conversations to be a little bit friendlier of a format like this, then we can basically set it up so that if you have your own conversational data, you can effectively plug it into this notebook and it should work just fine. So we have about 50,000 conversations, not too many, but a good amount. Again, recall that the Llama 2 had 100,000 of these conversations. Modern AI models will have more like 500,000, if not more than 1 million of these conversations. So here I have about 50,000 of them. Now, down here is where I define my special tokens. Now, again, in real life, this is all done for you. You download a chat model off Hugging Face. This has already been done for you. But I'm going to do it from scratch. I take these 3 special tokens, which I made these up. They could be whatever you want. I add them to the model, in this case, Llama 3, 8 billion. I add them to the tokenizer with a special add tokens method. Then I'm going to load up this model in what's called a quantized format. There's slides on quantization towards the end of the slide deck. And I explain this a lot in my other books. But very, very long story short, quantization refers to the reduction of precision of the floating point parameter values. Meaning, in normal time, basically normally, most numbers in computers are represented with 32 bits. 8 bytes is 8 bits is a byte. So 32 bits is 4 bytes of knowledge, of information on your RAM. So to hold a 32-bit floating point number in memory, you need 4 bytes of free space, okay? Multiply that by billions of parameters, it's not gonna fit. So what you do is you quantize. You reduce the precision of those parameter values to something like 4 bits is quite common, or 8 bits. But it can go down even more to 2 bits, or even the crazy people out there will do 1-bit parameter values, which is literally zeros and ones as parameters. A question coming in here, by the way, from NV. What are the pros and cons of writing it all by yourself as opposed to the other libraries to save that 75% of code? Completely fair question. This is not something I would ever do for a client, put it that way. In fact, given your question, what I will take the time to do on this repo is I will effectively add the version of this that is the 75% reduced code. So the pros of doing it this way is what some people would say is complete control. But that's, for me, it's not a good enough response. I'm only doing it for educational purposes. I can show you what's happening as low a level as I can. But to be honest, to be very, very honest with you, most of the code that is skipped over, that 75% reduction in code, is code that a lot of decisions are being made for you. So I'll call that out where I can. So for example, adding in my own tokens like this is not really something you would ever really do because you're probably going to be using a model off the shelf, which already has these special tokens built in. But if you were OpenAI, which I'm not, they have to do this. Like, they have to run this level of code to get their special tokens inside of the model. They don't get to do the 75% reduction in code because they have to do this. So I'm basically showing you what OpenAI does to get a model off the shelf for you. So our data set, our conversation, I hope that answers your question. We load up the model in a quantized format. And by the way, another question here, also from NV. What's the difference between LoRa and quantization? Good question. They are very different. Quantization is the reduction of parameter values. LoRa is a decomposition of weight matrices at any precision. So normally you do both together. It's called Q-LoRa. You quantize the model and then you decompose the quantized matrices. So you are performing fine-tuning in a quantized space. So you end up with a fine-tuned quantized model. So they are different, but you often do them together in a fine-tuning run. A related question, how do you choose how many layers to train with LoRa? Long story short, do all the layers unless you physically cannot fit that in your GPU, in which case try to go for half of the layers or a quarter of the layers being trainable, and specifically pick the layers towards the end of the model, the end referring to in a forward pass, the layers that would get activated towards the end, fine-tune those, don't fine-tune the ones in the beginning if you are going to make that choice. But I generally recommend you just, if you can fit it in your memory, to fine-tune all the layers if you can. So given this, I have my data set, which is multilingual, by the way, and I'll show the before, in which I asked who was the first president of the USA in the format. I get a ridiculous answer like the one I showed you here. So when I do my fine-tuning is going to look very similar to the BERT training, where my data set is going to be conversations in which I concatenate the conversations to be a single string. Now, this might look weird, but again, if you go to Hugging Face, go to that same Quine model, and I'll go to a different model, just for the sake of difference here. Let's go to that Gemma instruct model. So that's the IT, stands for instruct, which, to be very clear, if I remove that, another model exists, which is a non-instruct model, which is not a chatbot, only downloaded 300,000 times, whereas the instruct one, which has a chat image or chat inference here, has been downloaded 5 million times in the last month. Did you just not respond? Excuse me. Oh well. Anyways, if you click here on chat template, this is how complicated chat templates have gotten. This is a 347 line file, which explains all of the different special tokens that they have for things like tools and reasoning, thinking. Here is the declaration down here for tool calling. Here is the one for function calling down here. Here's where you have your human roles, your assistant roles. All of this is basically the modern version of me just concatenating my special tokens to look like this. But this happens under the hood. So this would be part of that 75% reduction, which is if I just use their chat templates, it'll work. But if I don't have a chat template, I have to make one up. I use my special tokens to delineate the difference between a human and a bot speaking. So when I ask the AI to predict something, I'm giving the AI a piece of text that is a representation of the ongoing conversation, given my template with special tokens telling it who is speaking and when. And you'll notice at the end here, I have this bot token. That's basically how autoregressive models work. I give the autoregressive model this context, and it gives me the next token as a classification problem. Then that next token becomes input for the next token, and then the next token, and then the next token. And it just keeps doing that over and over. So here, instead of training 8 billion parameters, with LoRa, I'm only training 54 million, less than 1% of the total size. So AA is asking, is QLoRa worth it? 100% yes. 100% yes. As I said, and I would argue it is a top 5 discovery of artificial intelligence in the last 10 years, which includes the invention of the transformer architecture 9 years ago. Like, it is up there with the transformer, because LoRa works with any deep learning model, like diffusion models, which there may not be time to get to today, but diffusion models also benefit from LoRa, which are non-transformers. So to do the training, I create a custom collator in which I want to make a loss that only runs on the final bot message, not on the entire input. Now, part of that 75% reduction is this already exists. There is already a class for this. I'm just showing you what it's doing under the hood. It's basically taking the input, finding where the bot token is, and only setting the labels to be the final bot response. Everything else is set to -100 instead of the token value. Why -100? I happen to know, because I worked with PyTorch for so long, that -100, if you read the documentation, -100 is a special case in which the loss functions in PyTorch will ignore that token when calculating the loss. So I'm just setting the token value to -100 for every token I don't care about. Then the loss function does what it's going to do, given the special value, and calculate my loss for me. Great. So I set up my data. I filter it so it's only the smaller sizes, just for the sake of speed. I'm still left with over 50,000 conversations here, so that's good. And then everything looks the same. I set up my training arguments, one epoch, a batch size, which is a little bit smaller because the data is a little bit bigger, another learning rate, load best model at the end, save and evaluate every epoch. Warm-up ratio means that the learning rate will actually start at something very close to 0 and increase up to the value I set in the first 10%, that's what 0.1 here. And when it falls, after that 10%, it will decrease following a cosine schedule, meaning it will kind of curve down and not linearly drop. I give it my model, my training data, my validation data. I have to give a tokenizer, my training parameters up above, and my custom data collator, which is doing the loss specifically for the labels that I care about. So I evaluate at the end. Note, there is no accuracy. This is not really a classification problem, or rather a simple classification problem. Accuracy is not really going to be super helpful here. loss is what we are relying on. Every deep learning model has a loss, but not all of them have accuracy. So learn to deal with a loss function. Now, the other hard thing about loss is there's no units. I can't say 1.5 is like a percentage. That's not true. The loss function is just a calculation of error. So you can't really put a unit on these numbers. You just have to say the loss was 1.5. After one epoch, the loss dropped to 0.97, which again, the loss by default is cross-entropy token classification. We can look at our weights if we want to. Here is one of our weight values. So now if I ask a question, same question, who was the first president of the USA? Now I get an answer, George Washington. This is transfer learning. This question does not appear in the data set. I promise you, I checked. The word president barely appears in the training set of the conversations here. I am relying on the fact that this model has seen data on the open internet and knows now how to answer questions given my chat template, my albeit very simple chat template, and answers the question. I can push that, which I have, so it's on Hugging Face if you ever want to try it out yourself. I can re-download it, use it again, and everything works. Yay. So again, it's a fair amount of code, do not get me wrong. And again, my book basically does this example in like 2 or 3 chapters, kind of like hand-holding along the way. But that's what OpenAI has to do, or Meta has to do, to make their models go from not being a chatbot to being a chatbot. It's not that much code, I would argue, and a lot of more recent packages will abstract away a lot of it. But basically what that means is they're just making decisions for you that they're basically saying, you probably were going to do this anyway, so we're just going to abstract it away for you. Okay, moving on. For the sake of time, I want to just kind of briefly mention some of the remaining case studies. Those were the main case studies I really wanted to do with language modeling. The ones I will also point you towards in multimodal, and yes, I have an entire lesson just on multimodal. What's mostly interesting about multimodal deep learning is, I would argue, in the diffusion process, which is one of the 5 types of multimodal architectures are maps from one data mode to another, like Nano Banana. Text to image is a classic multimodal type of architecture. And the way that these models produce images is not through language modeling, or not through generative autoregressive language modeling, and it's not even necessarily through transformers, but in fact through a process called diffusion, which I would like to explain actually briefly here on what diffusion actually is. Now, I will admit, this is going to be a bit of a mind twister because it's a completely different kind of task than language modeling, but it's still deep learning. So here's how it works. Image generators, I'll stick to image generators, do not generate images pixel by pixel, kind of like how it's a next token prediction. It's not a next pixel prediction. Instead, what they do is they start with completely static images, and they iteratively remove noise from that image until it looks like a thing that we can recognize. That sounds crazy, but that is actually how diffusion works. And I'll tell you how it's trained. It's actually kind of it's very elegant once you kind of wrap your mind around it. Here's how it works. The process of removing noise from static, we call P. And notice how P has a little subscript here, theta. That's almost a clear sign that this is a deep learning model, what we say parameterized by theta. Theta represents all of the parameters in a deep learning model. So here's how it works. The map to add noise, we call Q. So given a noise, given an image, I can add noise to that image. That's easy. So Q is how much noise we add at every single step. P is how much noise we remove at every single step. Here's the concept. Adding noise is easy. It's easy to add noise to an image. But is there a map that reverses the process? Can we go from a noised image and remove some of that noise? Here's the theory of deep learning once again. I have shown that a function could exist that removes noise from static. It's just the opposite of adding static to a noise. And what does deep learning promise? An approximation of any function. So if we parameterize this, in theory, we can construct a deep learning model that will perform this backwards diffusion process, which is what it's called. Here's the step-by-step. What you do is you pick an image, like a real image with no corruption. Pick an image, then pick a random noise sample, just noise, just literally static in the pixels. Then you pick a noise step where 0 is no noise, and then you pick a maximum number like 3, which is all of the noise, some of the noise, some less of the noise. Pick an amount of noise, and then literally add, plus sign, pixels, add the amount of noise to the original image, and you get something like this. Okay, that's the easy part to remember. So image plus a particular amount of noise equals this slightly corrupted noise. So how do we then use that to construct the backwards process? So instead of trying to predict the original image what you can do is train a model, most notably a UNet, which is a type of convolutional neural network, a neural net which takes in as input the noisy image, the image with noise added, the amount of noise that was added. And if these two are the input, the output is what was the original noise? What did it look like? Meaning you're trying to predict this thing. But we know what that answer is. Our training data knows what the original amount of noise was. So in theory, we can train a UNet predictor to take in a noised image, an amount of noise, and it will output the original noise used to make the slightly noisy image. I know I'm saying noise a lot, but that's the term that most people in diffusion use. So if we can do this, this is the training. The UNet takes in those two things, outputs a prediction. There is an actual noise that is being predicted. So then we just have to predict it, or rather see how similar they are. This is a regression problem, and it uses mean squared error, a loss I mentioned earlier for regression, mean squared error on the pixel values. See how close it was to the original noise. If that UNet works, this is how images are generated with Nano Banana or any other image generation model. It will start with a noisy image. Now, and again, in a later slide, it also adds in text input, like this is the prompt of what I am trying to do. But the general diffusion process is you start with a random piece of noise. You then tell it you're starting from, let's say, this is a parameter you can set when you generate an image. I forget what it's called. I think it's called like inference steps. Usually it's something like 50. In this case, it's 2. You start with 2. Input into the UNet, it will predict the predicted noise sample. Given that predicted noise sample, because you know that the original picture was the subset of the noise, in this case, this one, added, you can then subtract it to get a slightly denoised image. And then you decrement your noise amount by 1. Feed that into the UNet, you get another prediction of the original noise, you subtract it from the one you're at now, and you keep doing this over and over and over again until you get your final image at the end. So you parameterize the inverse of forward corruptive processes using a deep learning model. I know that's a lot to take in only like 5 minutes of explaining, but this is deep learning at work in other domains. Instead of text to text, now it's got to be, well, how do you go from a noisy image to a clean image? This whole process, by the way, is the brainchild of some very smart researchers who basically, on a hunch meaning an educated guess of many decades of training, said there must be a way of us being able to generate nice looking images from static. Can we think of a clever way to do this? And then someone sat down and said, well, if I can add noise to an image, why can't I train a deep learning model to go the other way? That's it. That's the aha moment in image generation that was had about 8 to 12 years ago, depending on the research that you're looking at, and saying this is it's not the only way to make images, but it's now the dominant way that people make images. And later versions of the UNet also take in a prompt. So it's not, now it's just the noise amount, and your prompt of what you are trying to do, but it's still the same process. You output a prediction of the noise, and you do that iterative step every single time. 15 minutes left. I will walk through one more example a little bit later on in our slide deck around reinforcement learning. It does like time permitting, and I do want to at least mention it for 5 minutes before I answer some final questions and end for the day. In reinforcement learning, you have a slightly different approach to fine-tuning the deep learning model. In a reinforcement learning loop, and again, yes, I have an entire 4-hour lecture dedicated to reinforcement learning. You're welcome to come to those. In a reinforcement learning loop, you have an agent, not an AI agent like you see in the news. This is a term of art for reinforcement learning, which has existed for decades. So I will respect the field and use their term of art as they define it to be. An agent in reinforcement learning is, hand waving a little bit here, any deep learning model. Most deep learning models. It's a deep learning model, to say it a different way. Again, your hint here is theta. The existence of theta implies this is a deep learning model where the parameters are being referred to as theta. Reinforcement learning says, you give the agent something to do. You let it do it. You may not have the answer to that question, but you do have a way of telling the AI when it's right or wrong. That may sound weird, because if you don't know the answer, how do you know if it's right? Well, let me put it this way. There is no single right answer to the question, what should an AI say when I simply say hello to the AI? That answer doesn't really exist, because that's not really fair. You can say a lot of things in response to hello. But I can say, well, hi is a good one. Hey is a good one. Hey, how you doing is another good one. I can come up with infinitely many good answers, but even easier is I can train a model to recognize good answers to questions. So instead of saying this is the right answer, I can say your answer is this good or this bad. If you have a way to do that, what reinforcement learning often will do is something like this. You give a language model a prompt. You ask the original language model, like off the shelf, what the answer is. Then you ask your version, which is about to be updated, the same question. You get two different answers, one from the original, one from the agent, the thing you are fine-tuning via reinforcement learning. Now, reinforcement learning is deep learning, meaning there's a loss function. But the explanation of the loss function will take a while. It's down here at a very high level for what it's worth. And you'll notice, maybe, some of the acronyms look familiar. KL, DKL. Huh, I've seen that before. Oh, right. Sinan used it in our very first example with MNIST. It's the Kullback-Leibler divergence. Reinforcement learning with language models generally have two main components of the loss function. One is we want the model to get better rewards, meaning the output of the language model is being passed through a secondary system, which is itself often a deep learning model, which gives a reward for how good the answer was. That's one component of the loss. If it's a good reward, you get a lower loss. If it's a bad reward, you get a higher loss. The other component of the loss function is often a Kullback-Leibler, which is defined as a distance of distribution. A Kullback-Leibler is a distribution difference, meaning at a high level, how different is this distribution from this distribution? And in this case, distribution are token distributions. The original language model gave this distribution of probabilities for its vocabulary. The new one gave this distribution of probabilities for its tokens and its vocabulary. The goal of Kullback-Leibler is to say how much it has diverged. And loss generally says, and the researchers will say, you don't want the model to go too far away from its original version. Someone asked a question, AB says, does this mean the model will forget something? And they asked this about 20 minutes ago when I was talking about fine-tuning my chatbot. But even in reinforcement learning as well, anytime you update a parameter of a deep learning model, you run the risk of that model forgetting something, which is why models tend to be so big, because the researchers, are aware that even when they update their model with new data, they don't want the model to forget the old data as much as possible. So the model is bigger than it has to be so that they know they can fit in more data as more data gets created every day. So models are big in part because the researchers are foreseeing adding more data, and to add more data risks forgetting something. One way to mitigate that is to have a bigger model, more parameters, more room to remember things. It's not a perfect guarantee, but it's just one of the reasons why models have become so big. Semi-related question, how do you avoid overfitting with LoRa? The easy answer is you assume a larger rank, meaning you decompose the matrix into something slightly bigger, meaning you're training more parameters, you're using more memory, but you often run the risk less of the model having to overfit on your training data because it didn't have many parameters to pick from. So increase the rank is the easiest way to avoid overfitting of LoRa. So I'll stop there with reinforcement learning, but if you are interested in what it kind of looks like, there's a version of the slides, not version, later in the slides, I do reinforcement learning on that same model I trained before, but we already did step one. Then I fine-tuned a reward mechanism based on human labeled data in which I would train a model using, for what it's worth, negative log likelihood, one of the losses we saw at the beginning of this class on the MNIST data set, to train a deep learning BERT model to know the difference between what a human labeled as a 9 versus what a human labeled as a 3. So I trained the model to basically classify which one of these responses to a question is better as dictated by a human. So then, when I do my reinforcement learning on that model, it went from a base model to being instructed, so meaning it can now answer questions like, who is the first president of the USA? But after the reinforcement learning, where I show it examples of how to answer a prompt, and I grade it basically with an AI specifically fine-tuned to match human judgment. And there's a GitHub for that in our there's a code for that in our GitHub. I'll admit, for what it's worth, I'll share my screen for a hot second here. In the code to do the reward training, which you can find in many places, including one of my books, A Quick Start Guide to LLMs, if you look at the code for training the reward model, here, all this code is, again, educationally, all the same stuff that OpenAI did. You can also use in Hugging Face's TRL, which is their, it stands for Transformers Reinforcement Learning, but really it does more than reinforcement learning, that all of that could be done in a few lines of code these days if you assume the basic stuff that I assume in that notebook. So if you give the file in the exact format they're expecting, you have to follow it, it will train for you a reward model without you getting to choose any of the hyperparameters. So again, this is what I mean when I say, yeah, there are versions of this where if you don't want to make any choices, it'll just make all the choices for you. It can reduce 75% more of your code. But there is a healthy balance of knowing what decisions are being made on your behalf and not wasting time coding a lot, which for what it's worth, Claude is a pretty good coder these days. You know, to code up one of those notebooks with the right machine learning engineer at the helm should only take like 30 minutes at most. So with the advent of AI-assisted coding, you just need to be the smart one in the room, who knows all the deep learning literature, and tell the AI what to do. Okay, with only a couple minutes left, a couple more questions here I'll do before I kind of give the rest of the case study overview. NB asks, sorry, can you again explain how you answer how it was able to answer who was the first president? Assuming there was no web search, which there was not. Again, so it's the transfer learning. I assume it saw on the open internet, because what I downloaded was the base version of that model, meaning it's not the randomly initialized model. It was the model that had been pre-trained. It read Wikipedia, it read Reddit, it read all these different sources of internet data, and then it transferred that knowledge to how to be a chatbot. So it answered my knowledge question based on knowledge from pre-training. Please recommend paths on O'Reilly to move forward on deep learning and data science. They also said I found my course interesting, which I appreciate. Yeah, of course, you can read my books on a quick start guide to LLM, and even my Building Agentic AI book has LLM as agents fine-tuning examples. There are actually some of those case studies can also be found in the book, in the slide deck here, where I talk about fine-tuning a model on openly available FAQ datasets. Off the top of my head, I can tell you that one of the best books for and classes on O'Reilly for deep learning is by a guy named John Krohn. I'll spell his name here. Johnchkhrohn. He wrote a book called Deep Learning Illustrated, which was a New York Times bestseller it's a bestseller on AI in general as well. Very, very great. Basically, what I did in 4 hours, he'll do in like 200-300 pages with a lot more visuals, breaking it down even more step by step. So he has a very good book on that. I would also, from there, take a look at more fine-tuning classes. I have more specific fine-tuning classes as well on the O'Reilly platform. Get more of the linear algebra explained by me. You know how you can get that on O'Reilly? At the form you're about to see when I turn things back over to Shannon right now, she's going to give you a survey. Tell that survey if you like this class or not. Please let me know what you liked and what you didn't like. Don't get me wrong. Also say in the additional comments, I wish you would get more into I want a separate class diving way more into the math. Because quite honestly, the higher ups, they shine against it, mostly